All right. Good morning. How's everybody doing? That was kind of weak. How's everybody doing? Nice. Welcome. Welcome. The crowd has thinned out here at the Computer History Museum. We're about maybe half the size as we were yesterday. It may have been the music and experience of DJ Poet last night. I'm not sure. Online, we want to welcome you guys as well. We've been getting some kind of tweets and messages from some of you guys, especially kind of in Europe and the far corners of the globe, who are like staying up all night with coffee, trying to like stay alive and alert. So wanted to welcome you back to day two. I'll introduce our first speaker, and as you guys know, the first half of the day we're going to have some main room sessions, and then the afternoon we're going to break into a couple of different tracks here, and some of that will be live streamed. So we're looking forward to going deeper with you guys today. So our speaker this morning is Janos. And Janos has done a lot of crazy things, including working at DARPA. He was known as the Arnold Schwarzenegger of DARPA. And his last name is Stepanovic, but I kind of remember it with Janos, son of a bitch, because he's kind of a badass. And he is, you can ask him later, but he was inducted into the Hungarian kind of Academy of Sciences, and along with some folks that some of you probably know. I don't actually know a lot. But anyway, so he's here to talk to you about some of the software tool chain that we're in the process of developing that you saw a little bit about yesterday, to make it super easy for you guys to make modules without going through the usual headaches of prototyping and failing and prototyping and failing. So with that, let's give a warm welcome to Janos.
Good morning. My name is indeed Janos Stepanovic. I'm director of the Institute for Software Integrated Systems at Vanderbilt University, and also I'm one of the co-founders of Metamorphing, who is developing the Metamorphosis tool suite. So my job today is to talk to you about the role of tools in the design of Ara, and I want to convince you why it's vitally important. So first, I will talk about what are the main challenges, what's unique in developing tools for Ara. The second part will be I go through some general concepts that relates to the composition of the tool chain, and elements of the tool chain, how we talk about it, how we use it. Finally, I go to the third part, which is a quick summary of the Metamorphosis tool suite. It will be really a quick and dirty rundown of the different elements, how the general concepts are showing up in this, because this afternoon at 1 p.m., we will have a 1.5-hour demonstration and discussion in which you show you the current status of the tools, and we'll also talk about how we would like to start up the alpha testing. So let me get on it. So first, what are the general concepts here? Well, as you know, you remember from Paul's talk, design comes up in two different flavors. One is of course, Ara. One is the design of the Ara components, where these components are software, apps, drivers, and of course, the hardware modules. The second part is the design of configurations. Design basically Ara systems. We all know that part of the design happens in the user space, so it's awfully important to end up with another design which is beautiful, exciting, flexible, and most of all, yours. Now, it's quite appropriate, frankly, to tell you that Ara in Hungarian means bride. So that's all of the features what you want to have from a bride. But to be beautiful, exciting, flexible, and yours comes with some caveats. What are these? All of the user expectations have to be satisfied. It would be extremely annoying if you put together the modules, you start up the system, and it locks up. It would be awfully annoying if the functional requirements of the individual modules and apps will not be met because of interference from other modules and apps. Also, it's very important that the phone, after configured, will provide guarantees for satisfying safety and operational standards. Now, there is absolutely no way that every conceivable configuration of this phone will be pre-verified deeply and shown explicitly that all of these requirements will be satisfied, simply because the practicality is that the number of combinatorics is working such that the number of configurations is practically infinite. So what can we do in these cases? Well, we have to go to the first part of the design, which is the design technology for the Ara components. There are two major trusts that are used for guaranteeing the delivery of the promises. First of all, I need to tell you that all of these requirements, that user expectations are satisfied and safety security requirements are met, means that the name of the game is not only to provide and enable interoperability across the modules, but you have to provide compositionality. Compositionality means that properties of the individual modules can be used for compute and prove the properties of the overall system. It's a very hard call. This is one of the perennial questions in software design. How can we create framework in which compositionality is met? So coming back to the design technology, when we build up the Ara modules, all of the modules need to satisfy the design constraints, design requirements, what the Ara platform defines. These design constraints are primarily responsible for provider compositionality. These design constraints will introduce restrictions how you have to design the software and the hardware components. But you gain a lot with it, simply because that will be ultimately the guarantee that the system will work together with the other modules. Now, who will enforce all of the design constraints? That's where the tools are coming in the picture. So all of the tool suites that are produced for other module developers and software developers are designed such that you can verify that all of the constraints that needs to be satisfied by the Ara platforms are indeed satisfied. And that will require occasionally quite deep analysis and methods that are theoretically sound. Now, so ultimately at this point we know that we have to have some kind of design methods, and these design methods need to provide evidence that the platform-defined constraints are all met. But what's further special in this whole issue in the Ara domain? Well, the most important thing is that Ara is a so-called cyber-physical system. A cyber-physical system means that you have an engineering artifact, and functionalities and salient properties of that artifact are emerging from the interaction of physical and computational processes. Your car is a cyber-physical system, and not surprisingly, Ara itself is a cyber-physical system. What does it mean to design a cyber-physical system? In the Ara context, of course, you have to move around along different design concerns. You have to see how can I design the circuits. You have to show that the circuit, what you design, fits to the mechanical constraint. You have to look into the RF interference issues. You have to show that the RF emission is not too strong and will not interfere with the other components, the sensors that might be sensitive to RF emissions. You have to deal with the software. You have to show that the software, what you design in the apps, doesn't have deadlock. And it doesn't have deadlock even if you compose it with other components, with other apps, even if they use shared resources. You have to look at the timing properties, because some of the apps, together with the appropriate hardware modules, will be subject to hard or soft timing restrictions. And of course, you need to deal with the thermal behavior. You have to be sure that the modules will not overheat. But beyond this, the major problem is that if you look all of those design concerns, you see that everything is interacting with everything else. When you try to get a solution for the timing problem, it may interfere with the earlier solution what you gained for the thermal behavior. Thermal behaviors may interfere with the mechanical layout. The mechanical layout interfere with the way how you design the circuit. All of these interactions pose a really complicated so-called cyber-physical design problem. The issue here is that the holy grail in engineering, the separation of concern, is not working very well. If you isolate all of these things, you address separately all of these design concerns, where it will turn out that you made mistakes. You neglected the interactions. When in the customer space, when you configure the Ara modules, and it hangs up, it overheats, because of reasons that you just neglected totally the interaction. And that's really not a good place to be. So ultimately, the design toolchain role is to deal with and guarantee compositionality, at least for critical properties that may be damaging if it is not there in the user space. And the second is that you have to do it such that you pursue a genuine cyber-physical design. When you take an integrated view of all of these different design concerns and track all of the interactions across them. Now, clearly what's emerging here is that something needs to be done with heterogeneity. Now, let me go back to a point what Ken brought up yesterday when he kicked off the conference. And this is the so-called DARPA DNA. The Metamorphosis tool suite has a very strong DARPA DNA. In fact, it grew out from a program called Adaptive Vehicle Make program, what Paul created at DARPA. It was started in 2010. And the objective of that program was a design technology for a cyber-physical system that is roughly 10 to the 6 larger or heavier than an Ara module, which is an amphibious vehicle. But that doesn't look amphibious, but that was the objective. So now, what was the design approach for this? And what was unique in it? When you start up the design of a complicated vehicle like that, it's very reasonable that you start up it such that you go to an older design, take it apart, analyze it, draw the conclusions, and then come up with the new elements. You come up with new solutions, new components, you integrate the design, finally you build a system, build a prototype, test it, figure out where the requirements are not met, go back, redesign, build, test, redesign, build, test. That's the conventional way to build these systems. Of course, it's awfully expensive because it includes a build phase. It locks out a very large part of the design community because you have to have manufacturing facilities to build a prototype. And ultimately, it's a very lengthy operation. So the idea in the program was that there will be another phase introduced in the middle of it, and that phase is the phase of models. After we conceptualize what are the components of the system, we take these components, we model those, and start the process which is a model-based design process. We take the models, integrate the models, compose in the virtual space, a virtual prototype for the overall system. We check the requirements computationally and continue the iterations. After we are sure in the virtual world, in the world of the models, that the design satisfy all of the constraints, then we can go on, send the whole design package, the design data package, to the manufacturing facilities, and they build it. Now, if the technology is strong enough, then the predicted behavior of the models, based on the models, will correspond quite closely to the system as it was built. And that's the whole issue in the program. How can we build up that technology in which we can do the whole design evolution in the virtual space? Now, clearly, the impact can be quite astronomical. The prediction was that it's reasonable to expect that the design productivity will grow about 80%. It can be expected that if it's done, we can build a clean interface between a fabless design environment and the manufacturing place. So we can pursue that kind of development style, which is very common in the VLSI industry. There are fabless design houses and foundries in the cyber-physical system domain. And finally, the whole issue came up very strongly that if that technology is available, how can we so-called democratize the design? Which means how can we provide inexpensive tools, engineering tools, for a very large community so that they can get innovative and they can be players in a domain from which they were excluded before. So that was basically the key idea of the AVM program, and many of the points came out from the AVM program and the Meta tool suite, which originated in the AVM program. So altogether, the technology challenge, what we have to face is the following. There are two major thrusts. One is the model-based technologies. The model-based technologies means that we want to conduct the design such that we use computational models, and these computational models has to have enough fidelity that you can predict the properties of the cyber-physical system as designed and as manufactured. So it's a pretty tall call. The critical element to achieve improvement, dramatic improvement in model-based technologies is to understand what are the right abstraction layers what you have to use in the design process. And of course, to create design flows that can be supported by a number of tools. The second essential part is the so-called component-based design. Component-based design in this context means that you decompose the overall problem into knowledge chunks. A component model is really nothing else, just a reusable design information. It can dramatically decrease the cost of the overall design, and indeed the productivity increase to a large extent comes from the existence of high-quality component model libraries. Well, the problem is that in the same time, you have to understand how can I provide the required compositionality, which means that when I glue together the different kind of components, whether they are cyber or physical or cyber-physical, I can precisely compute what will be the properties of the created system using the models. And that type of compositionality really is a very hard problem to solve, and the program had a good progress in it. Now, let me finish with this DNA issue. So many of the things emerged from that program, which was running for 4 years, and it's now in the transitioning phase to different systems companies. In many ways, what we are doing in Metamorphosis is also part of the overall transitioning effort. So what is the overall meta approach in this sense? What you see here is a rough flow. It tells that the design flow will start with a component library that provides the design reuse. In this component library, we take advantage of many cross-domain type of information about the components. So we can do really an integrated overall design. We take then the component library and create a design space. You create a design space. You tell what are the architectures that you are interested in using these components that are available, or using some new components, what you want to design. When you created this overall design space, you traverse it. You evaluate the points in the design space. And during the evaluation, you use a number of tools that make these evaluations. The important point is that you follow a progressive refinement strategy, which means that you start with rudimentary architectures, simple properties like static properties, but a huge design space. It's the conceptual phase. You do the evaluation, and while doing the evaluation, you trim down tremendously the size of the space. Then you proceed with more detailed analysis. You start focusing on behavior. These are more expensive analyses, but you have to do it on smaller design spaces. And then you progress toward the physical design. When you do the finite element analysis, you do the really expensive, highly involved calculation, but now only focusing for a small number of targets. A critical element of this overall process, what you see on the right side, which are the so-called virtual test benches. These test benches are manifestations of requirements. Each requirement category, what you need to check, is associated with a test bench. You can then instantiate the test bench, link it to the design and the design spaces, and run in a loop these evaluations in a highly automated way. So that's the overall picture of the design flow, and that's what you will see popping up at the demonstration and later what I will talk about also. Now, when you want to implement that concept, you will really need to use a number of existing tools. There's absolutely no way that in a cyber-physical design project than Ara, we will redevelop all of the critical tool elements that do these evaluations. They are high complexity tools that evolve decades and represent a huge value. These tools are available occasionally commercial off-the-shelf, versions of commercial off-the-shelves that are released for community use and free, and also available in open source. Some of the hardest design problems, some of the hardest verification problems actually are associated with open source design tools because they are evolving for very long. There's a huge academic interest in it, and universities, research institutes, research groups are quite frequently produced highly usable open source, open IP tool suite. Of course, we are extremely interested in these because one of the very important goals is to support an open community, an ecosystem, the individual designers who may not be able to afford to buy 20,000 or 60,000 per seat engineering tools, obviously. So we will have here in the underlying infrastructure a number of design tools, again, some of them open source, some of them are commercial off the shelf. And of course, we need to do the development of an appropriate framework underneath that will support the integration of new tools. You can expand it, change it. You can take always the best of class tools. And you also need to be able to provide flexibility to expand the overall design space toward different disciplines if the focus is shifting. Let me talk now about another important challenge, which is heterogeneity. So heterogeneity in a cyber-physical system design obviously is what kills everyone. There are many sources of heterogeneity. If you look at the overall design space, we can look three different dimensions that brings in heterogeneity. One is the hierarchical abstractions. When you move on that axis, when you move upward, you do abstraction. When you move downward, you do refinement. When you move upward, you are representing larger and larger systems. But necessarily the models that you use there has to be less and less high fidelity, simply because nothing would scale anyway. So that brings in a heterogeneity in terms of fidelity. But there are other sources. Let's do the other dimension, which deals with the different design domains. roughly we have to talk about the physical design domains and the software design domains, or computational design domains. But if you look at the physical design domain, there are many different phenomena. There are electrical phenomena, mechanical phenomena, there are fluid dynamics if it is needed, magnetic, and others. So clearly, that brings in a lot of heterogeneity. First, the cyber and the physical heterogeneity, and second, the phenomena-generated heterogeneity. Now, the third axis, which is the design abstractions, really relate to the mathematical foundations for these models. Some of the models, some of the abstractions what we use are simple static characterizations. Some of them use discrete event semantics. Some of them use ordinary diff equations and continuous time semantics. Others are using hybrid dynamics. Then there are, of course, designs which require detailed knowledge of geometry, finite element behaviors that are described with partial diff equations. So altogether, there is a quite broad range of different abstractions that define all different kind of mathematical domains that impact how you design the system. Now, it's very common these days that different tool suites are designed such that they take a slice and provide a vertically integrated segment in this overall space. So, for example, you can find tool suite for ECAD, you can find tool suites for dynamics, lump parameter dynamics, you can find tool suite for finite element analysis combined with CAD, you can find pure CAD, but what you can find is this: the whole cyber-physical system design space where you would like to move around freely and seamlessly. And don't forget that it's important because everything is interacting with everything else. And when you particularly deal with very constrained systems, like a phone, the penalty what you pay for modularity is coming primarily if you are not able to follow all of the interactions that are coming from the constraints across the design domains. So that's why this is a critical element. The other general source of heterogeneity, of course, that tools what you use have their own life cycle. They represent a very particular view of the artifacts. They have a philosophy how you should design. They have different formats. And still, these different tools have to be integrated in an overall design flow seamlessly. Now let's go and review some of the core concepts that are important in the overall cyber-physical design space. One thing is the so-called model integration concept. Model integration, I try to use this slide now, which is a complicated slide for a lot of things, so I hopefully will not get lost. Model integration means the following. When you build a design and you use a number of tools, all of these tools are looking at the artifact what you are dealing with from different point of views. They use their own design language, modeling languages. Then when you talk about the overall modeling problem, you may take the position that the modeling problem means that I use the modeling languages that are nothing else but the union of all of the modeling languages what all of the tools are using. This is clearly an impossible issue, right? Because it's complicated. Every one of these tools have very complicated and occasionally not even very nicely defined internal semantics. It includes rather a lot of experience and rule of thumbs and so forth. So it's just a complicated, messy problem. So how can we simplify it? How can we express then in this environment interactions across these different modeling disciplines? Well, one way to approach it is that we develop a concept that allows out from the individual worlds of the individual tools just a segment of their semantics, just a segment of their modeling concept. just enough to describe the interactions across the different models. That can be a much smaller, much narrower defined subset of the overall semantics what the tools are using. If you do that, you can express that precisely. I use here the term metamodel, which is the meaning of this is some way of modeling the models themselves. And it models, the metamodels models basically the subset of the modeling languages, what you need for disclosing something about the internal semantics of the tools. And then what we do with this? We combine all of these together using a so-called model integration language. The model integration language exports all of these disclosed subsets of the semantics that are coming through a well-defined semantic interface, adds additional concepts that are needed to describe now the interactions across, and basically comes up with an integrated model set where the integrated model set on one hand includes all of the domain-specific models captured and built by the tools, plus includes the interaction models across this. The interesting point here is that when you design the model integration language, your goal is not universality. You don't want to design a language which covers everything. But you want to design a language which is the simplest possible what you need to describe the essential interactions. Okay? So this is a very different kind of mindset than what you would follow when you are the designer of a universal language. For example, like SysML wants to be one of these universal languages, or UML is one of the universal languages. So it's much more scoped, much narrower, but there is a price. It has to be dynamic. You continuously have to change the integration language, right? Because the tools are changing, your interest is changing, you have to factor in new tools and kick out other tools. And that means a very interesting and hard concept. It means that we have to design a model integration language which is continuously evolving. And the only way to keep soundness of a language like this is that you explicitly represent the semantics. Now, that's another part, what I will not go into details, but a very essential part of what we are doing in Metamorphosis. And this is the so-called concept of semantic backplane. The semantic backplane basically is an explicit representation using some form of logic. All of the semantics of the modeling languages and the semantic interfaces. That formal system, what we use, is coming from Microsoft Research. It's the work of Ethan Jackson. The tool is called Formula. You can see it, download it. It's an open source tool. We systematically represent for all of the tool elements these semantic interfaces for Formula, and the only way how you see them, and the only point when it pops up, when you want to look up reference manuals. These reference manual, which provides you the precise concept language constructs, what we use in the integration language called sci-fi ML, are auto-generated from these Formula representations. If you are very much interested in the deeper semantics, then you can download Formula and play with it, and it has an execution semantics, and you can run interesting studies with this. For example, checking when you are composing the integration language, haven't you created by chance any contradictions inside? So all of the composed languages are semantically consistent or not. So that's the overall model integration concept. And you heard about it. Sci-fi ML is the model integration language. Sci-fi ML is as simple as possible and always covers the need of that special domain or set of domains what you want to represent the interactions across. Now let me go on and talk about not only the languages but also the models themselves. There are three categories of models what we deal with in Metamorphosis. One is the component models. The component model, you have to imagine it as a container. That container lumps together a bunch of things, all of the important information about a component. it can have many different kind of models hidden inside. What's important is that the interfaces are very precisely defined. We have four categories of interfaces: the parametric interfaces for every component, the structural interfaces that belong to the geometric composition of the components and represent the geometric constraints when you link together and connect together in the 3D space components. Signal interfaces that are causal interfaces that represent signal flows in the system, mainly for the software and the cyber parts. And the power interfaces, where we represent the physical interactions, which are acausal interfaces. There is a cast iron component model, what Metamorphosis defines. That component model, that Ara component model, is what we use overall when we are constructing different kind of Ara designs. The second part is the designs. The design models are taking the component models and link together the components into an overall system using these interfaces. Obviously, there is a lot of constraints what the system, which helps you to do the composition, will enforce. There are different kinds of type constraints, different kind of physics-rooted constraints, geometric constraints, and the architectural design tool, which is part of the overall tool suite, knows about this. It will be checked again and again, and that's an essential part of checking all of the compliance of the designs with what the Ara platform dictates. And finally, there is another concept, which is the design space models. The design space model means that instead of just dealing with a point design, which is a totally instantiated set of components linked into a particular architecture, in the design space model, you represent classes of designs, whole spaces of designs. How can you enrich a point design into a design space? There are two basic ways for it. You take parameters, mutable parameters, and define ranges for it. With that, you can get a parameterized design. The other part of it is that you can, for every component, or for those components where you want, you can introduce structural alternatives. And these alternatives provide you a set of possible architectures, what you are interested in. So there is a method, and there is an internal representation scheme and language with which you can define also design spaces. The whole thing is hierarchical and of course, compositional. You can compose a system, and you can turn a composed system into another component, and you can deal really with the design spaces as if it were virtually a single component, but it's not. It's a complicated set of alternatives, parameterized, and has many different possible manifestations. Now, an important concept, what we understood on the way, is the design space construction. No one will give you a design space. It's you who are deciding it. One naive way to approach construction of design spaces would be, if I have a stack of components, my design space is really nothing else but all of the possible combinations of the components. If you would construct this way a design space, it would be hopeless, because almost all of the points in that design space would be meaningless. So instead of following that strategy, we followed the other one. Take a seed design. That seed design might be one of the other reference designs. Take that seed design as a template and enrich the design space around it. Introduce parametrization. Introduce alternative components. And go in that as you like. Define your own space of interest. And when you construct the design space such, then you can define a very nicely and efficient design space exploration problem, which then will be executed in a highly automated way using the test benches. So that example, what you see there, is how it shows up when you construct a subpart of design space such that for a processor you start introducing 7 different alternative selections. But at the demonstration you will see detailed example how to do that. We talked about the test benches and the ultimate importance of the test benches. The test benches are basically configurable experiments. These are computational experiments with which you check certain performance parameters, certain metrics, what you need to know whether your design is satisfying or not. There are test bench libraries. These test bench libraries are associated with different requirements, different requirement categories. You can use them. And then when you have a design or a design space, a full design space, you can take the test bench and you plug in basically your design or design space. You wire it up into the environment. And then there is an automation mechanism which takes that and runs the evaluations for all of the design points that are in the design space and transmit you the results on different kind of visualization tools. Now, the last point what I would like to touch as a basic element here is the so-called integration framework. So if you see all of these things what we were talking about, the different tools, the different kind of models, the automations and everything, one can imagine that, yes, if you give me 20 or 30 massive tools, I can somehow wire them together, patch them together, and hopefully the whole thing will work for a while. There were many experiments, I have to tell you, in the aerospace industry and in the automotive industry, how to do these complex integrated design flows. And many of them failed for tremendous expense. And we believe that the source of the failure is that integrating design automation tool suite is in itself is a very complicated problem and requires platforms. In Metamorphosis, we use 3 different integration platforms. One is the model integration platform. I showed you what is model integration, and what you have to take away that the model integration platform is that layer in which we take care of the modeling languages, the semantic connections between the modeling languages, what are the semantic interfaces, how we express the interactions across these different kind of models. And after I design a full system using component models, how I can generate an overall integrated model from the architecture specification. That's all the business of the model integration platform. It's reasonably abstract, but tool supported in itself. The second layer is the tool integration platform. The tool integration platform is really nothing else, just a bunch of model transformations. These model transformations are taking out from the component model the particular kind of behavioral model, let's say, what you need for a test bench. It goes then to a design composer. That design composer takes information from a design or from a design space and synthesizes the overall integrated design model using the behavioral models that are coming from the component. And then there is a whole suite of individual model transformations that take the overall integrated design model and generate inputs for the constituent tools. They feed tools that deal with simulations, CAD, finite element analysis, and so forth. So ultimately, the source of all information which drives the individual tools is an integrated model suite that belongs to architectures. And of course, the advantage is that it can be highly automated. The third layer, finally, is the execution integration platform. Now, we learned that many of these integrated design tool suites are very complicated even from deployment point of view. The tools have different life cycles. Some of the tools require tremendous computational power. And it's not surprising that the only deployment model, if we would stick with the desktop integration as the only execution platform, it wouldn't scale all that much. Although it may be possible that particularly at the beginning, the Metamorphosis tool suite is coming out to you as a desktop runnable, downloadable system. But we learned from this background program that when the design tool suite is getting very large, it may be worthwhile to deploy these high complexity tools in the cloud and provide access through some kind of web interface to the overall analysis process. And indeed, we have versions of that tool suite which is also cloud deployed or also desktop deployed. Now with this, I basically covered the most important conceptual point. We were talking about cyber-physical systems. What does it mean? What's the source of heterogeneity? Why do we need to deal with this? How can we guarantee compositionality? What is the complexity related to checking compliance to Ara platform requirements? And then we went on and looked how to manage heterogeneity. What does it mean? Model integration. What does it mean? Test bench. What does it mean? Component model, design model, and design space model. And how can we run test benches on full design spaces? And finally, as you see, we have an overall layered integration platform which addresses these issues separately and deals with model integration, tool integration using model transformations, and an execution integration using different style of execution platform. Now, after that, we can go to some elements of the Metamorphosis tool suite. Again, I will browse that through mainly because I hope you are interested and you can see it in the afternoon demos, how they show up and what is their status. And again, as I mentioned, we are actively recruiting now good souls who have patience, who are compassionate, and are willing to do alpha testing. Now let's see the Metamorphosis tool suite. So basically the Metamorphosis tool suite are comprised of these three integration layers. And in these three integration layers, we take a specific configuration of design languages, integration models. We bring in through the tool integration layer a set of open source or COTS software tools that cover a broad domain for cross-disciplinary analysis. In Metamorphosis right now, the primary deployment strategy is desktop integration. But as the tool suite is evolving, changing, and expanding, we may want to change it to cloud-based deployment. So that's the overall Metamorphosis things. So when you ask, so tell me, what is the Metamorphosis tool? Well, you will see a bunch of things. Tools that relate to these integration platforms, libraries that relate to these integration platforms, and a number of tools that are other tools that were created in different parts of the world. Some of the most valuable open source tool suites are coming from research communities in Europe and research communities in the US. So it's really a complex but integrated set of resources that you can use for Ara design. The roles of that tool suite is summarized here. So you can model, analyze a cyber-physical design in one integrated, preferably open source package. We cannot promise that everything will be open source and totally free, because simply there are areas where we could not find alternatives for it. The tool suite role also to consider a range of different component choices and architectures, not only individual designs. So it means that when you do a design process, then you can do optimization immediately. You can figure out what is the best alternative which satisfies all of the requirements and provides the lowest cost, the fastest, or the shortest shipping time variant of it. There are tools with which you can do multi-objective optimization, excellent graphical tools with which you can see how the evaluations are running and where are the design points in the different performance metric spaces. Another role of the overall tool suite is to test and verify, of course, critical properties that are defined in the Ara platform. Another role is to synthesize a manufacturable design. So what comes out from the whole design process is a design data package, a product data package, what you can take away, and hopefully it's complete enough that it can be plugged in and the module can be generated out of it in a highly automated way. And of course, in the whole process, an important goal is to leverage component, circuit, and module library or model library, and that really cuts back the time what you need to spend for coming up with a new module design. Here is a set of design phases during the design process you will go through. You start with curated component library. Curated component library means that all of those component models that are in the repository are satisfying the constraints that are defined by the standard or a component model. The key elements of these repositories are platform components, off-the-shelf components, user-defined components, and of course, seed designs or reference designs. The next step is that you go to an architectural exploration phase. In the architectural exploration, the first thing is you define your design space, as we were talking about. You can expand now the space around reference designs, and after you ended up with the design space, in which you use, of course, the appropriate modeling languages, the Sci-Fi ML, model integration language, and the design space construction methods, you do evaluation. You check module fit, the mechanical constraint, you look the bill of materials for the individual components, you check lead time and cost. You use all of that information to trim down the design space to a manageable size. After that comes the set of behavioral evaluations. The behavioral evaluations use appropriate test benches. These test benches embed tools. There is the Android emulator, development kit, the Android System C bridge, the System C behavior and timing models, SPICE behaviors and signal models, or Modelica behavioral and for thermal models. The behavioral models are integrated. You can represent cross-domain interactions, and you can run these evaluations with the underlying test benches such that it provides you the designs taking in consideration all of these cross-domain changes. Finally, you go to the physical evaluation phase. In the physical evaluation phase, you deal with really issues, the geometry, schematics, place and route, different CAD models, and you can use these CAD models for thermal analysis, RF analysis, and whatever is needed. And finally, you have a product. The product is in an overall integrated technical data package, and it includes the software, the bill of materials, the printed circuit board specification, and different metrics that are coming from the test benches, what you can pack up and use. That's the instantiation of the overall layered architecture in the Metamorphosis tools chain. Ultimately, it's exactly the same than the generic architecture what I showed you. The very large parts of the integration architecture and the integration platforms are inherited from the previous projects. The only thing what I would mention here is what is on the left side, which shows elements. What are the native components that belong to the integration layers? So, for example, if you look at the model integration platform, there are meta models, ontology specification, and meta-programmable tools. These are coming and belong to the underlying model integration platform. For the tool integration, you see model transformation, semantic interface specifications, and test bench libraries. These are technologies and tools with which, let's say, you can design your own model interpreters or model transformations when you need it. And there are different kind of tools, schedulers, deployment services, storage services that belong to the execution integration. Ara needs, of course, well-defined component model. These component models include behavioral, geometry, software, circuit models, data sheets, documentations, interface and connector information. So basically, when you see an Ara component or a metamorphosis component, this is a container of all of this information, but with well-defined interfaces, strictly defined interfaces. So here is an example that for a chip, you have a number of these different kind of model elements, information sources, from schematics, data sheet, software interface, circuit behavior, thermal behavior. All of this is wrapped together in a component container. That component container, again, has these strongly defined interfaces through which you can access parameters, power, signal interfaces, and structural interfaces, and use it for describing overall system architectures that can be analyzed further. The Metamorphosis tool suite has a suite of test benches. Here are the currently existing test bench types. Chip fit for mechanical compliance, constraint compliance, semantics, behavioral timing, power simulations, and others. You will see that all of that during the demonstrations in the afternoon. The test benches are referencing different MDK specification requirements. Obviously, what we are doing is that we go through on the requirements what the MDK imposes, and then we build the test benches for it, which verifies that indeed your design meets those. The final topic that I want to talk about quite briefly is the verification approach. Because many of the design includes an integrated hardware-software and hardware-software interactions. This is clearly a very important point to understand, is there any contradiction there? How can I verify that the hardware-software interactions don't create unintended side effects? If the resource limitations, shared resources, is not creating deadlocks, if all of the timing requirements are specified. Now, these studies are complicated enough that there is absolutely no way that you can just release on them, on the full design, formal verification tools, and then they give you back the results that it's pass or fail. So this is a relatively complicated issue, what we are right now working on, how to formulate a verification strategy for hardware-software interactions that is scalable, and we follow basically a staged strategy. Again, the goal is to do verification on the application and module level. We need to verify the firmware for interface compatibility, behavioral requirements, power usage, the software drivers for interface compatibility, compliance to protocols that are required, timing properties. We need to verify also system-level issues for device sharing, resource usage, and so forth. So there are clearly a rich set of verification opportunities that we intend to address. The overall approach what we follow is that we use the so-called TLM, the transaction level modeling approach. It means that we will have a standard library set, what we want to develop, which provides an abstract System C specification for the key components of the platform. It provides the high-level specification, abstract specification for the whole Android stack, the communication stack, and the whole bridge between an application and the hardware module. These high-level specifications are simple enough that it neglects a lot of details, so it's not a detailed design specification for the whole stack, but a high-level interface specification, which leaves out a lot of details. We also recommend that when you do your design, the application module design or the hardware design, you come up with a System C, high-level System C specification for this, what you can refine further. When you plug together the system, we have tools that you can do the composition for it, and you can run simulation, integrated simulation. That's already existing, and you can see it. But it's also good for another purpose. The overall intended verification flow looks like that you start with the abstract model, then you translate the abstract model into model checking tools like time automata checking, UPAL or SPIN. You run verification, check behavioral properties for this, and check basically the consistency of the overall specification of your model, whether it's consistent with the behavior of the abstract behavior of the platform itself. But after that, we go over to another things as the design progressing. We change over to hardware in the loop simulators, and basically we auto-generate the full test bench, which then checks whether or not the specifications, the requirements, what you started with, will indeed be preserved, and that will be done using a test-based analysis. So this is the end. If I compare the traditional design flows and the metamorphosis design tools, then let me emphasize again the following. In the metamorphosis tools, instead of using separate models and isolated tools, we create a single integrated model, and we use multi-model analysis. Instead of using disconnected and inevitably high complexity, expensive engineering tools, we go after integrated tool set, and wherever we can, we use open source tools or community releases for commercial tools. We use the design space concept as a first order concept, and we propose that you always conduct your design such that you consider a number of alternatives, explore it, and come up with an optimal design. We integrate the workflows of designer, analysts, and manufacturers, and hopefully that integration will be quite effective overall. With this, I ran out of time and I finished my presentation. Thank you very much for your attention.
All right. All right. Thank you, Janos. You and your team are super modelers. That's incredible. There's been some proposals that we just scrap the rest of the program and have Janos and our good friend yesterday just do a panel together, because that would be the best use of time. But anyway, let's get a couple of questions from IRC. We're going to hold off on questions in room, so just find Janos later on if you want to go deeper. So Rip asks, how much of this tool chain is supplied as a common tool, and how much, if any, represent opportunities for tool vendors? So I think the question is, they might want to expand, extend, adapt.
Yes, the integration platforms are designed and documented such that other tools, tool components can be integrated into it. So they are internal open interfaces, there are methods how to do that, and that's frankly one of the important goals of the structuring that those tools, the overall space into specific integration platform. Just a comment on this. NSF, the National Science Foundation, will use this integration platform as a delivery platform in the Cyber Physical System program for researchers who are developing open source tools. So that's one aspect of it. But tool vendors also are encouraged and will be encouraged to come up with ideas and integrate into the tool suite they are approaches. Yeah.
Kind of aspect of it. All right, cool. Second question is from Yari 2. He's asking, why do we need to care about cyber-physical design methodologies? And he says, I actually do care about this stuff, but he's saying I doubt a lot of other people do. Why don't we just do something simpler and just provide Arduino Shield-like references for 1x1, 2x2 model, and models of the major different module types?
When I was talking about that everything is interacting with everything else, there are two ways to handle it. One is done in the platform's restrictions. You decouple the design space, right? You introduce the shears. You want to decrease the tangledness of the design space, but you cannot do it to extremes. You cannot do it on that level that every design concern is decoupled from every other design concern. Or if you do it, you pay such a performance penalty what you cannot afford. So at the end of the day, what's left? Or you pray to God that when the modules are configured, the customer will not get a locked up system, or you do a cyber physical system design flow, right?
Awesome. Okay, last question is, what is another term that you can kind of add to our vocabulary that's as cool as cyber physical?
Metamorph Inc.
Okay, awesome. Thank you, Janos. Amazing. Okay, great. Okay, so for those of you that are, grabbing some paper to get ready for this next challenge, this is not going to be a paper tower building challenge again. We're going to bring Paul back onto stage to talk to you about ways that we're trying to inspire and incent the community to do some awesome stuff. He's going to talk about our developer prize challenge. One last note. Our new IRC channel is Ara DevCon Day 2. We kind of had maxed out the Ara DevCon IRC channel, so Ara DevCon Day 2. Although for this next session, we're not going to be doing Q&A. It's a brief session, but we'll start the Q&A afterwards for the hardware panel. Thanks. Welcome, Paul.
Thanks. All right. Hey, guys. Slides? Great. Okay, so I wanted to give a little bit of a preview about what we have in store in terms of developer price challenges, as well as how to get hardware. That's been probably the most frequently asked question yesterday. I don't have all of the answers for you today, but I will. I'll give you our current thinking again in the spirit of transparency, as promised yesterday. And we're probably a couple weeks away from having sort of very definitive terms for both the prize challenge and the hardware loans. So this is an info briefing. Please read the rest of the disclaimer there. The goals behind the prize challenge are mostly to incentivize, obviously, new entrants into the module developer ecosystem. And also to promote the diversity of module concepts for us as a community to collectively brainstorm, like, what are the kinds of things that don't exist in phones today that are uniquely enabled by the Project Ara platform. And obviously, as prizes are prone to do, we hope that it expands awareness of the MDK and of the ecosystem. We have to get to critical mass for this to become a viable product. And it's also a somewhat systematic means and a timeline for us to get hardware out to the developer community to start working with. So the general format we think is going to look like this. So the first thing that a developer needs to do is send us a relatively brief abstract. It'll probably be something like a page or two that describes what it is that they want to do. And they'll also need to agree to basically a loan agreement that the hardware is returnable to us. We may or may not ever actually ask for it back, but there will need to be an agreement associated with it. Now, the developer hardware that we would provide isn't actually required, right? You have the MDK. You can instantiate the MDK through whatever means that you choose, that you prefer. And David did a very nice walkthrough yesterday of sort of some alternatives, right, for how you might instantiate different parts of the MDK with different levels of customization that you might be interested in. Now, the advantage of the developer hardware that we would supply is that that it will contain FPGAs. It will include the FPGAs with the Toshiba RTL, that provides the bridging function as well as the switching function. So it provides a fairly easy way to accurately represent and develop around a representative network architecture. In the end, what we want, obviously, is a functional form factor module around this prototype hardware or your own prototype hardware. We will test the module in some reference canonical endo configuration with a set of other modules. So we'll have an AP module and a display and other things, and it'll need to work. So you'll have to develop a driver and any apps necessary to functionalize the module. We will use the TI, the OMAP 4460, as the reference application processor. And so that you can develop your driver on a Panda board, or you can develop your driver on the dev boards that we would supply to you. And there will be a description of the hardware in the next. That's the next session. What we are proposing is 100K to get things started. We do plan a series of these throughout 2014. So first prize is 100K. The two runner-up prizes are that will cover for a small team. Will cover your travel expenses to the next DevCon, and will guarantee you hardware, so you don't have to write up an abstract. You don't have to apply or whatever the process ends up being for the second prize challenge, which will be in the fall. And we'll probably have much more substantial prize cup associated with it as well. The judging, ideally, right? So DARPA has a long and storied experience with prizes, and the best kinds of prizes are prizes where the criteria are completely objective, and the entrants can actually self-judge, right? They can self-evaluate against those criteria, so they know how they're doing and whether they're on a vector towards improvement. Unfortunately, that's very difficult to do when the kinds of things that you're trying to accomplish are diversity, right, and novelty. And it's also difficult to do when you're working with prototype hardware that, as I showed the numbers yesterday, right, isn't terribly power efficient, isn't terribly space efficient. It is functional, and it does allow us to prove out the Unipro network, the power system, the EPMs, and all of the long poles in the tent as we see them for the platform. But it's hard to squeeze out performance from prototype hardware. So as a consequence, we've tried to articulate some objective criteria, but a bulk of them are unfortunately qualitative and subjective, and I'm not sure that we have a way of getting around that. For the subsequent prize challenges that I mentioned, that I alluded to for the fall, we will make them as objective and quantitative as possible in terms of metrics. So you see our current draft of the judging criteria. So we want things that we want modules that are likely to be in daily use, right? So things that are likely to be ubiquitous, and also things that you currently can't do on your phone. And so we'll try and assess those. Obviously, we'll flesh out the definitions of those and try to assess those as sort of Boolean judging factors for the prize. And then a set of qualitative criteria, novelty of application, so sort of how creative is it, the quality of the technical implementation, not the least of which is does it work, and then the sort of the scale of impact of the application and the path forward, right? So what do you plan to do to bring that to actually bring that module into the ecosystem and make it available? And again, we'll define these much more crisply in the official prize rules. So here's a brief timeline. The 0.10 MDK release was April 9th. We are here on April 16th, and you'll see a preview of the developer hardware in just a few minutes, just as soon as I get off stage. We should have developer hardware available in quantities of about 100 to 200, sort of depending on the configuration that you're interested in. We have more of some things than other things. Available by early May, so in a couple of weeks, it's in the process of being fabricated. We will issue another MDK release, and that is a typo. It will not be the 0.20 release. It'll be like the 0.12 release or the 0.11 release. fix any errors and incorporate some of the feedback that we get at this afternoon's feedback sessions from you all. And by that point, we should also have our Android repository available so that you can check out a full build for the OMAP 4460. And so that'll be mid-May, and we intend to announce the challenge in mid-May as well. So we will come out with sort of much more detailed set of rules. Everything will be communicated through projectara.com. So you'll see a new tab materialize on the website in the coming weeks. That'll be price challenge, and all of the documentation and the announcement of the price challenge will be there. So that'll be our principal means for officially communicating the rules and the announcements and the launch. Then we'll give you a couple of weeks to start sending us abstracts. It'll actually be a rolling kind of thing, so that if people come up with a module idea a month from now or 2 months from now, it's totally fine. We'll hold back some hardware to make sure that we can support those. But the earliest you'll be able to get it is probably late May to early June timeframe. And then we intend to keep the price challenge open until about early to mid-September, at which point we're going to start working toward the ASIC version of the MDK that's based around much smaller, much tighter, kind of more production ready module templates and interface hardware. So that's the rough timeline. And actually, I think that's all I have. We will obviously, you all registered for the conference, so we have your contact information, and unless you explicitly opted out from receiving any future communications, we'll give you a heads up with a targeted mailing that says, hey, the price challenge coming tomorrow or something like that, or check the website. And as I said, that'll be our principal medium for announcing it, but we'll tweet about it. You'll hear about it. You won't miss it, I promise. And that's what we have planned. I'm not going to take questions, not to be evasive, but basically because that's all I have to say. And so I'm not sure that I can offer any additional detail at this juncture. There are lots of, as you can imagine, there are lots of reviews that have to happen on the official rules and hardware loan agreements and things like that. And we've been so focused on the MDK and the Developers Conference that we just haven't churned through all that. So stay tuned for a couple more weeks and take a look at the hardware. Ask lots of questions of the hardware panel in terms of what functionality there will or will not be in the developer hardware. And there'll be ample documentation available for it as well that the team has been putting together, and that'll also go up on the website just as soon as it's ready. So that's all I got. And if we're not, are we quite ready for the developer panel, or should people take a brief break? 10-minute break, yes? Okay, so take a 10-minute break. They're setting up some hardware and a way to project for everybody to be able to see the hardware demos. And we'll be back with a panel. So thanks very much.
Hello. All right. All right. All right, folks. So we're going to get started in 5 minutes. Just 2 quick announcements. John Park, we need you to get mic'd up, so come on back. And for those that are clustering around the hardware stuff, just give these guys a little bit of space and time to set up. You guys will see what they're doing very shortly. All right, 5 minutes. Mike. Isn't it great?
So, Daddy, how did you learn to be such a great MC? I suppose.
My mom's an actress.
Oh,
My
okay.
dad. All right, folks. Everybody, please, let's take your seats. We're going to get started. Everybody, please take your seats, especially those around the hardware area. Our Google security guys do know Kung Fu, and you've got another minute or 2 to sit down. You guys ready? Okay. All right, guys. We good? Okay, welcome back. We are now going to have a panel talking about some of the folks that are working on components and pieces that are making its way into the developers kit. They're going to give you some examples about what's possible. Elwin is going to introduce some of our folks on our panel and kind of facilitate some Q&A. Again, our IRC channel is Ara DevCon Day 2, and you can also just tweet at us, #AraDev. And we'll leave some time at the end for about a couple of questions, depending on how much volume we get. All right, welcome Elwin and panel.
Thanks, Daniel. All right, so we have a few presentations prepared for you to start us off and give you an overview of the hardware we have available. We're going to start with Marti Boulevard. Actually, let me introduce everybody first. Marti, you guys met yesterday. Bertrand Lee is from Lattice Semiconductors. And then you guys met Seth yesterday from NK Labs. And finally, we have John Park from AQS. So Marti's going to start us off. We got the presentation ready? We got the clicker? Where's the clicker? Does someone have the clicker? No clicker on the board. All right. Here you go.
All right, nice. Can I get the mic? Okay. Let's see. Cool. Yep. So as most of you have seen already, we have 3 development boards for you. There's a processor board, which has an OMAP 4460. There's a switch dev board, and there's an endpoint dev board. And the purpose of the processor and endpoint dev boards are basically to get convenient, prepackaged boards for you to get the tunneling that we talked about yesterday. So that's native protocols like I2C, GPIO, tunneled through Unipro network, so that you can get your module development done without having to worry about interfacing with Unipro while the software and hardware work on that is proceeding in parallel. And the switch is, well, it's the switch. So this is the system architecture. It's kind of been beaten to death a little bit already, so I won't dwell on it. But yeah, you've got the 2 colored boxes where your stuff goes. The OMAP 4460 runs Android and whatever you want to put on it. The given arrows go into a bridge FPGA, which gets tunneled through the switch and pops out on the other side. Now, there are some cases, as we mentioned in the MDK, where due to particularities of some of the protocols in question, it's not a completely faithful tunnel, and it is documented in those cases what those deviations are. So, for example, currently a repeated start on an I2C bus gets transformed into a stop start on the other side. A little bit about the AP Dev board. It's got the Android build that we discussed yesterday, with a bit of extra support for app level I2C and GPIO access, and there's some demo apps which were available as part of the MDK, so you can kind of see how writing code for that looks like. The FPGA tunnels the native protocols like we just saw. The switch is technically optional for development. You could link the AP directly to the endpoint, but of course, on the final test for the prize challenge, there will be a switch present, so we recommend developing with a switch, test what you deploy. And there's a supervisory microcontroller on there, which will set up a routing table and handle communications, setting up routes between the AP and the endpoint dev. And the endpoint dev board has a variety of breakouts, in a few different connector styles, depending on the protocol. And you can check the schematic for that. There's, that does include some 10th-inch breakout header for simple cases, and there's also, SMA and more fine pitch, DSI connectors for displays. As Paul mentioned, it will be available soon. Watch projectara.com, and that's where all the updates are going to go, including hardware availability and the Android release, once we get all the dots and crosses checked out for code review. So that's all I've got. Thanks very much.
Actually, before we get to John Park, we have a demo of the dev board that I think we're really ready. Actually, we have a video showing something exciting. So Seth is going to introduce the video.
Do we have the video up? Oh, here it is. For the architecture for this first prototype and also for the dev boards, we have a tunneling interface. So we're taking our interface standards and tunneling them over Unipro. And the last and one of the more challenging tunnels that we've been bringing up is the DSI tunnel for display. Late last night, the team in Germany sent us this video. We've been video of the video. We have the AP dev board, which has the OMAP 4460 processor, has DSI1, that's a MIPI display protocol, and those DSI lines are connected to the FPGA. FPGA takes the DSI signal, converts it into Unipro packets, sends it over our packet switch network through the network switch over to the display endpoint. And there it is. We're booting Android and displaying it on a touchscreen through our DSI tunnel.
Very exciting.
So
yeah. And apparently it's 12:02 in Germany.
That's right.
So next we're going to go to the video over there and the hardware, the dev board setup we have over there. And I think, Seth, you're going to talk through that as well?
Yeah, we're going to turn it over to Dave to walk us through the boards that we have set up. He has the roaming mic.
Hello?
So over in our demo station, we have Dave and Mycroft and Perry. Our team has been staying up long nights for the last few weeks getting all this ready to show. So here it is. They'll talk you through it and show you how it works.
All right, here we have the AP dev board, the Endo switch, and this is the USB form factor module. All form factor modules have EPM controllers, so what we're demonstrating right here is that using an application, we'll be actually triggering the EPM enable and the EPM disable. So, you ready to go?
Yeah, let's go and wake it up.
Yeah. So, as you can see right now, it slides out pretty easily. If I lift this thing up, it'll just slide right down. It'll fall right out.
Yeah.
Yeah. You can lift this thing up, you can pull it out, and we can demonstrate an EPM unlock in a little while, but there's a little problems that we run into here and there. But yeah, so here we have the EPM locked in there. You can force it out, but it takes a little bit of force to do it. We'll show you guys in a little bit. All right. Thanks.
Thanks, Dave.
Thanks.
Are there other demos you want to show?
That's good. I wanted to say that these development boards have the exact same circuits laid out that we have on the small form factor phone. The same circuits, but we've spread it out on the circuit board, including a lot of connectors and test points in order to facilitate bring up and testing. And then we've miniaturized it and got all those electronics to fit on the 20 millimeter by 40 millimeter circuit boards in the form factor modules. We're connecting here with cables, but it's the spring pins in the form factor phone to connect the data lanes.
That's great. Thanks, Seth. And thanks to the whole team back there. I know you guys have been staying up late these past couple of days and past weeks, so I want to give a shout out to all of you guys. All right, so next we have John Park from AQS, who's going to give us a presentation on AQS and their relationship with Project R. Thanks.
Sure. Hi, my name is John Park from AQS. We are the manufacturing and hardware partner for this project. Our company is about 23, 24 years old, right here in Silicon Valley, about maybe 100,000 square foot, more than 200 people, and we've been supporting a lot of these new projects we call MPI. And then we typically starting from the engineering specification and then deal with the design and the logistic issue, and also, the design logic, and then the layout issue. At the early stage, what we are expecting when we say, okay, specification, what that means is we are the factory, so we need to make this product, all of those products made out from our factory right here in Silicon Valley. And then this is the most scary moment when we see this, oh, please, it has to turn on. If it doesn't work, it's all my fault, because we didn't do right. But actually, a lot of these things starts from the very early stage of design. we would like you as an engineer, when you start the design, you need to think about this is final product, we have to make it. So when you design, you need to select the right components. And also, I mean, we had a great lecture, just the professor. But the fact is, if you don't consider all these components availability and the lead time, and plus, if you don't have enough experience, we will have a lot of difficulty when we actually do the manufacturing. And obviously, if any one of you would like to trying to design some modules, yes, we have a lot of help available in Silicon Valley, and also plus we have Ara and SES, all great teams available. We are willing to help you. So, and then after you finish your design, another important thing is a PCB layout. This one, we're dealing with the product itself. It gets lighter and thinner and smaller. And also, we need to worry about the lesser power consumption and also the heat issue. And a lot of these things, you need to select very carefully when you do the PCB layout, what kind of materials, and the quality of PCB itself. One way to simplify this kind of issue is when something happens with many different people together, you have a trouble to pinpoint who made what mistake, who select which component, which the layout or PCB manufacturer. So we can simplify that. You do when you finish your schematic design, you could ask your CM, your contract manufacturer, to do the actual PCB layout and be responsible for the PCB itself and manufacturing all the way. So that way, if any liability or some difficulties, you know, and you have only one person to choke. Otherwise, especially this one, we use a component, we say 01005, which is like a dust, like you can just blow away. It's so tiny. You can't even see it properly without it's a very, very small components. So all those things you need to consider. Mechanical part, yes. We will use quite a bit of 3D printing, the mechanical parts, and supporting by the 3D system. Yes, that's a good way to do it. And then, after that, we got to put this together in perfect angle, tolerance and everything. So when you do the industrial design, your designer has to have a clear concept about this, the tolerance issue, and this, especially for the initial stage, we will use a 3D printing system to make the components. So maybe many ID or MD mechanical engineers not familiar with the 3D machine system production level. So that part, your engineer must take the consideration, that part too. Okay. And the next step, what we do is we do the two-step we call DFM, design for manufacturability. After we receive your design, we'd like to make sure all these the parts are routed properly. And then usually we like to check this twice before the production begin. But as you know and we all know, many times, very often, especially MPI stages, most important issues are timing. You know, we spent the last couple nights here at the factory, and it's just like we are fully awake now, right? By this time, we spend so many nights, and then everybody wants to get the job done so fast. So we really need to have you need to have your true cooperation and collaboration, work very closely with your CM. Otherwise, you're going to make mistake. And then especially this Ara module is highly technical. Many CMs is not used to. So always give us enough time to check all the routing circuits and everything, layout, and then no sharp turns, and then not too close, all these things, and make sure that all the components twice before we get into the production. And this is a typical example of DFM staging. What we do is once we receive all those components and then everything's ready and we run through the program, or you can do it manually. But what this does is basically trying to pinpoint, okay, we believe this spot, this area, or this line is going to cause trouble, what we believe. Then we raise a red flag, and we will contact your design engineer with our processing engineer to either resolve or negotiate the problem. Sometimes you don't have a time. You have a big demonstration in front of maybe a VC or to your customer, so don't have a time. Or sometime, okay, let's go redo the job and then remake the PCB or whatever, or touch up, whatever. So all these kind of DFM, it takes a time, and then when we prepare this DFM, we would like to invite your engineer to our facility. When you choose your CM, we highly recommend to go visit your CM and work with them. It's just like if you, okay, I place order and then it'll get the job done some time down the road. It just doesn't work that way, especially the MPI stage. And that will eliminate a lot of potential mistake. So DFM is for us is very important. And then the one part we're missing is also we call DFT. Testing is another issue. When the board is fully assembled and then we believe everything's done, the next level is a testing. Sometimes testing takes more time for the new product. And often at early design stage, there's not even, you don't even consider the testing not. So we can't even test it, or it's so hard to test it. So in order to solve that issue, once again, at early stage, your design engineer and our processing engineer needs to work together. So at the design stage, when we make sure there's a testing point we put at the design stage, it will make life a lot easier. And after that, we got to have a testing program. Either you provide it or your CM has to provide a testing program to make sure this board is okay. Otherwise, the job is not done. And then the last part is supply chain side. This is just my personal opinion. What we believe that we need to lower the price point if we use, I think this is Ara phone concept is a great concept, and eventually this will lower the price point significantly. Then the issue is the supply chain. Of course, there is a high-end product, the extremely high-end product for maybe medical device or some testing device. Those kind of product is maybe price is lesser important. But for to reach the 5 more billion people trying to make a $50 phone, the supply chain would be very, very important. That's also you need to consider at the design stage. There's a lot of good parts out there. The price is not that good. But if you talk to your supply chain people, usually your distributors or your part provider, they could give you the choice. It performs very similar, but price can be quite different. So your CM and also your part supplier will tell you which component has a much lesser price, and also the lead time issue. There's a two-step approaches. When you make a first initial prototype, you just need to prove your concept, and your purpose is to convince maybe your investors or the customer. That time, you need to make the products as quickly as possible. But the second and third phase is, okay, we're going to go reasonably good volume or the massive volume, then supply chain will change completely. And that time, obviously, you need to talk to your CM, okay, we need to lower all the price, and we call sourcing. And then the price will go down significantly. So that's a supply chain side. And obviously, with the NK teams and then all the software hardware team, we are here to help. And then we would like to provide all the helps, whatever we can. And obviously, there is many other good CMs available in Silicon Valley. They are quite big, good, and some of them are quite better than us. But what's important is you need to find a CM, work together. And then there's a lot of services available, and what we can do is we'd like to provide a best available service from Silicon Valley, also from, you can see my face, from Asia. And also we have great partners in Europe and also India. So all these services are available. So if you have any issues, especially hardware things, please contact our support at aqsinc.com. Okay, thank you.
Thank you, John. So I noticed in one of your slides you had Gerber files. So as I have a 1-year-old, Gerber files means something completely different to me. So speaking of being a new parent and never getting enough sleep, you know who has less sleep? Ara and Seth and his whole team. So I know that John mentioned that we're here to help you, and we are, but not Ara and Seth's team. They have been working really hard to support this program, and so we ask that if you have any questions or anything related to the dev boards, that please do not contact them specifically. Please come to us or go through AQS. Their time is very valuable, and I'm sure on behalf of their families as well, that they will be very grateful that you don't contact them directly for those issues. So lastly, I want to go to Bertrand Lee from Lattice Semiconductors. We've heard a lot about the FPGAs that are in our prototypes, and Bertrand's going to talk a little bit about that.
Yep. Thanks, Erwin. I'm Bertrand Lee. I'm responsible for worldwide technical support for our FPGAs. So what an endorsement of FPGA being enabler for the hardware, quick turn hardware. Two of the areas that FPGA plays is ASIC emulation, quick turn hardware emulation, and I/O bridging function. So to that end, ECP3, Lattice ECP3 is performing that function where we are doing the UniPro stack within the device. On one side, on the back plane is the LVDS interface, and on the other side is all these interfaces that we talked about, DSI for the display, I2C, I2S, SDIO for various different interfaces. So, FPGA can perform many different functions due to the nature of the programmability. You have to choose the right FPGA to implement these functions. Lattice can help you with that. In terms of quick turn, John talks about at the last minute fixes in the hardware. FPGA is excellent. I do this all day long, working with our customers, and anybody who would be building hardware, last minute changes, we can do that through RTL and get to your hardware in hours to less than days. So we can support that. So I do expect that the UniPro stack, you're not going to be touching that as part of the predefined function, but as you build these modules, you will have to figure out how to interface to various different bridging. And we have many other FPGAs in the form factor and power. We have devices that are in the less than 2 millimeter by 2 millimeter in the microwatts of power. I'm not saying that it will implement the UniPro stack, but it can definitely enable some of the bridging functions. So with that, I want to acknowledge my colleagues from Lattice, also David, Brent, David, and Dan. Just raise your hands. We're here to help you. Come grab us, talk to us for the FPGA needs. Okay?
All right. Great. And now we're opening it up for some questions, either in the room or Daniel, do you have some questions from virtually? Virtual questions. We can give virtual answers.
So one of the first questions from Rip is, any plans to add support for other bridged interface standards? So audio specific as one example.
Does anybody want to tackle that one?
So presently, the interfaces that we have tunnels implemented for are DSI-1, SDIO, I2C, I2S for audio, and GPIO. In our plans for tunnel development, we are also going to implement CSI for a camera in the coming months. And we could also perhaps consider some other interfaces, although we are really focusing on migrating toward our objective platform, where these tunnels are intended for initial prototypes and concept demonstrations, but then we'll move toward our implementation of the class drivers in Android to drive these devices, and those would be provided for DSI, CSI, I2C, I2S, SDIO, USB, HSIC, and GPIO.
Okay, great. Next question from Harsh Khanna. would there be only one basic standard dev board available, or a variety of dev boards with different built-in modules? I think you touched on that a little bit in your previous
So
answer.
so of the dev boards that we're working with, we have the general purpose endpoint board that has SDIO, I2C, I2S, GPIO, and there's a selector switch on the board to be able to choose which of the interfaces are enabled on the FPGA. So you could, for example, have SDIO plus GPIO.
Okay, great. Megas Chara asks, will the dev board support Android's open accessory protocol? Marty, you want to take this one?
Well, let's see. So the Linara 1309 release that we based off of is on top of Android 4.3. So if AOA is in Android 4.3, which I don't recall off the top of my head, then yes, and otherwise, no.
All right. Let's take a question from here. You, sir?
Yeah, is the FPGA considered a closed module for the purposes of the program, or is the RTL going to be made available to module developers if they, for example, want to try to incorporate additional functionality into the FPGA?
So I think I'll take that one. So as of right now, the RTL won't be available to third parties. It's Toshiba proprietary information, and so the compiled bit streams will be encrypted, and we'll be just providing FPGAs to third parties who are interested.
Okay, so it's a closed module for at least at this point in the program. Okay,
That's
thank
right.
you.
Yeah, so that's for the development platform, right? As you go and build your own hardware, the bridging functions and things like that, those reference designs are available if you are choosing to go develop your own hardware.
All right, next question from online. Holo YOLO 420 asks, do you guys edit these names? What kind of built-in modules, hardware will be in the dev board, i.e. SD card slot, USB, networking, Wi-Fi?
Dave, would you like to take that one?
Hello? The AP Dev Board Rev 2 has 4 USB ports, 4 USB hosts. It has an Android debugging port that you can plug into your computer and do standard Android debugging. Ethernet, I2S audio codec. It has SD card for expansion, like SDIO expansion, HDMI, and has the LCD connector to connect to this specific LCD. And is there anything I'm missing?
SDIO to boot.
And all of that.
Oh, yeah, and Unipro, of course, yeah.
Of course, what, SDIO to boot, right? Is that what you guys want to say?
The GPN point has an I2S, I2C, I2S? It has I2S, right? Yeah, I2S, I2C, SDIO interfaces, GPIO, and I think that's, yeah, it has an EPM controller. Yeah, that's about it.
I think we'll make all of these available in the official documentation, so you'll know exactly what the interfaces will be provided, as well as the various other support mechanisms on the dev boards will be available. So those we will publish shortly. Nick Rout asked a question: will there be repairable or replaceable over voltage, over current protection in the dev board? If something were to go wrong, replacing these boards would not really be possible.
The general purpose endpoint does have dev board does have resettable fuse and over voltage protection. Some of our other dev boards have not yet implemented all of those safety features, and we are working on revisions of the hardware that will be much more user-friendly in the lab and more robust and more repairable.
Great. Let's go to the audience. You, sir?
Oh, yeah. I'm not sure if this is a good question for now or at the 1 o'clock industrial design session, but was there a reason between keeping the modules at 3 sizes, specifically the 1x2? And the reason why is, looking at the board, if you were to put that piece in horizontally and, for example, put a camera button on it, so that when people have the phone horizontal, they can snap a picture. Obviously, if you were to take that out and put it in vertically, that button either isn't going to make it fit, it's not going to work. And looking at the spec designs, there's also 2 sets of those connectors for the vertical design for the 1x2. So I'm just wondering, obviously, to keep it simple, so that if you buy a 1x2, you can switch it around, but 4 physical buttons for 3D attributes, have you guys given any thought to that design process and how that will play a part? And then again, I don't know if that's a better question for the one.
Yeah, I think that probably is a better question for the ID MDK review or feedback session later this afternoon, but thank you for the question. Other people, audience questions? Yes, sir.
Hi, I have a question for John from AQS. Thank you for giving us the overview of the manufacturing process. Just for the benefit of clarification, I would like to ask, would you expect most of these modules to be Type 3 or Type 4 designs? And can you explain to us what that means and the cost implications there? And also, is there a minimum order that should be expected from a CM in order to benefit of all these great services that you described?
I believe at the initial stage, everybody's looking for just a small volume, just trying to prove your concept. That's early stage, obviously, and this is open market, and it's not just the AQS. Anybody can make it. Whoever the CM can give you the better support, especially at the early stage. It'll be difficult for any CM to make a small volume. That part, yes, we could give you good support. But once it becomes, let's say maybe 6 months or 1 year down the road, and then some special, whatever the module, it becomes hugely popular, I think the market will dominate. Wherever the CM can do the better job at a lower cost, will dominate the market. So that's how I see it.
Great. Next question.
Thank you.
Over here.
AQS does have small.
I had a question about. I remember yesterday you mentioned
there's
the
no minimum order for this part.
device class drivers.
Sorry, can you repeat your question?
Sorry. So I remember yesterday you talked about device class drivers, and I was wondering if there's a one-to-one relationship between the bridge protocols in the Unipro and the device driver. For example, if a device fit in the display class, would it have to use like the DQI protocol or something?
The device class, is my mic on? Yeah, okay. So the device class drivers, the class drivers for the objective design are for modules that speak native Unipro. We don't envision those covering modules that are going to be communicating over bridge chips right now, except in the case of, like, let's say, USB class drivers that are going to be going through the USB host controller in the GP bridge. Does that make sense?
Seth, you want to add something?
Yes. So the different modules, while we do like to refer to a camera module and a display module, in the architecture, in the platform, we are not expecting that there's no requirement that an individual module have a single function. So you can definitely bundle multiple functions into a module. For example, a display module in our prototype We also includes the audio for a microphone input, buttons for power and volume control. The I2C touchscreen controller obviously is bundled with the display. So in fact, in a single module, we have many different interfaces going to different functionality within a single unit.
Great, thanks, Seth. All right, this may not be a tough question, but it's a tough name. 18VAAGPHB asks, FPGA is just to get Unipro running before it's supported natively, right? The FPGA is just to get Unipro running before it's supported natively, right? I think that's a yes, no.
So our vision for the Ara platform is the industry is moving toward adoption of Unipro. So we'd like to see application processors with native Unipro ports, cameras with native Unipro in the form of CSI3. But this is an emerging standard. There's not a lot of uptake today for parts that we can order out of a catalog that have fully integrated Unipro. So that's why we're implementing these bridges where we can take the interfaces of today and utilize the newer Unipro interface standard.
Right.
So
I think also the fact that Unipro and FPGA are not one and the same, right? You can implement Unipro in both FPGAs and ASICs, and so while we're using FPGAs currently because ASICs aren't available currently, right?
That's a perfect use of FPGA where we support the LVDS or M5 related interfaces on one side, and then we can go to any other interface on the other side.
Right. Any more questions from the audience? Otherwise, we'll go to the last question online. Ram asks, does Ara allow dynamic shutdown, wake-up, frequency scaling for power management? Ara, do you support that? No? No, OK. How about the Ara platform? Does it support shutdown, wake-up, frequency scaling, or for power management?
Yeah, I mean, that's inherent in the Unipro gearing is frequency scaling, power management, hibernate. Jürgen talked a lot about that yesterday.
Great. Thank you for the short answer. All right. I think, unless there are more questions, I think we're good. Thank the panel.
All right. All right. Thank you, gentlemen. That's fantastic. All right, it's going to take a couple of minutes till we get our next speaker mic'd up. And he is Shardul, I want to say crazy, but I think it's Kazi, or Kazi. And he is at Toshiba. And this next section, he's going to show you guys some reference module designs. So you saw earlier the pulse oximeter, and there's a number of other modules that we've been developing so that we can have reference software and hardware available for teams that are working on something that might be somewhat similar or can use as a starting point. So he's going to walk through some of those. I tried to get an interesting fact that very few people knew about him that he would let me release publicly to the world. And he was a little bit coy, so I'm going to ask you guys after the session for lunch to try to do better than me and get something really interesting out of him. I will say, however, that he's actually really into gaming, which you might not notice just from first appearance, and that he has, in his past life and in past work, has actually created some of the innards that have contributed to things like the PS, 2, maybe 3, some Xbox stuff. So he's a gaming enthusiast. So those of you that are looking at gaming scenarios, I'm sure he'd be happy to bounce some ideas off of you. All right, let's hear it for Shardul.
All right, good morning. So my name is Shardul Kazi. I think I'm the last speaker in this common session, and I'm standing right between you and lunch. So please give me 30 minutes. I want to go over and talk about the relationship which we have, which we developed between Toshiba and Google, and how it started, and where we are going to go from here. So I think the inception of this relationship started from the MIPI Alliance. But in November, I remember that we had meeting with Paul and his team, and then some of our team, we all met together, and then that was the first meeting, and then Paul went over the whole conceptual idea of this Ara project, and then we were all skeptical, and we were thinking about it, like where is this going and all that. And then suddenly he brings up a box, and that box, and with the white gloves, and then he makes us wear these white gloves, and then he opens the box, and the box had that endoskeleton and all these modules, and then we could take that and connect it and snap it and disconnect it and all that. And then that was the aha moment for us. And then we said that this is the concept which is novel concept, and we never imagined this type of things. And if any company who can take this type of concept into production, then it is Google. So we have to develop this relationship stronger and work together. So that was the, I think, the game changer concept which brought by Toshiba to now reality. And I think, of course, we think that this opportunity is going to expand our presence into the mobile world. It also, we seriously think that this concept is not going to stay only with the smartphone, but it is going to go beyond smartphone. So many devices will have this modular approach, and maybe you will be able to take the modules out of the smartphone and put it in some other device and get some functionality and all that. So there are many reasons why we are excited to engage into Ara program. But I think one of the other things why we are interested is this open platform concept. And later on in my presentation, I'm going to talk about it, because the barrier to entry in the mobile world is very high. And this open platform, by releasing things and sharing the knowledge, a lot of people can enter into the mobile world. And we are also going to do the same thing on the reference models. So I will touch that a little bit later. And the last but not least is the core competencies which Toshiba has in terms of capabilities in expertise, or even in IPs, Unipro, and those type of things are always the last things which completely match with the Ara requirements. And that's why we are all engaged into this program. So we have done a lot of things. I think, well, yesterday you heard from Jorgen that we are developing FPGA. You just had a panel and show the development board. But really, what we are planning beyond development board is we are developing 3 products here. One is a switch, which is at the bottom of the screen. And that switch is going to be part of the endoskeleton. And then the other 2 products which we are developing are the 2 bridges. And we call them AP bridge and GP bridge. So in the diagram, system diagram, that's in the center, you see the switch. And the switch is going to be, like I said, in the endoskeleton. All the remaining things are different modules. So for example, the top is a application processor, and that will be AP module. So application processor will connect with the AP bridge, and AP bridge will connect the switch. And similarly, you can see camera and display are also connected through AP bridge to switch. And then other peripherals, which are general purpose peripherals, they can be connected with switch using the GP bridge. So quickly give you a little bit more information on the bridge. AP bridge has CSI and DSI interface, and there are 2 CSI DSI interfaces. Each one is with the 4-lane D5, and there is a host bus interface, I2S, I2C, GPIOs. These are the common standard interfaces which are included on that one side of the bridge. The other side of the bridge, of course, is the Unipro, And then that is the switch side. So Unipro will connect to the switch, and the other devices can use the standard interfaces. And CSI, DSI are MIPI standard, and the other one are host control standard interfaces. So this bridge will be used for the modules for application processor, display, camera, mainly. And then the next bridge is the GP bridge, which is a general purpose bridge, which is kind of similar to the AP bridge, but it's a little bit simpler because it does not have CSI, DSI, camera interface, and display interface. But it has all the standard interface like HSIC and SDIO, UART, I2S, I2C, EPM, GPIO, etc. So that's the basic configuration. These chips are right now, we have been, since November, like I said, we started working with Google. We have defined the specification. We came up with the block diagrams, and now we are working on this chip development activity. So the functions are described here mainly for the chip. I think AP bridge has a Unipro interface, which is yesterday you heard a long presentation about Unipro, and Unipro it basically covers all the Unipro standards. It has CSI2 interface, DSI interface, host interface. There are two host interfaces. One is HSIC, which is assumed for now, and then the other one is going to be parallel memory interface. We are still defining the specification of this. There is an embedded microprocessor in that, which is used for the internal data transfer and control mechanisms, and then, of course, the standard interface like I2C, I2S, etc. are there. So that's the AP bridge, and similar information I have here for the GP bridge. So those are the mainly bridges. I think the system-wise, this configuration with these bridges can be, like basic configuration is shown on the left-hand side. The basic configuration means there is one camera, for example, and one display and application processor. Of course, this modular approach is, phone can be very simple. It can be just AP processor and a Wi-Fi module and a display. But if you have more peripheral, that is what we call basic configuration, because it uses only one CSI, DSI channel. And then, of course, as the more feature you want to add, you can have dual camera or dual display, and then the more features can be added, more applications can be added to this. This diagram quickly showing the data flow. So if you see CSI single use and DSI single use, then, for example, one camera will capture the data, and CSI RX, or receiver, will get that camera through camera interface, that data. That data will go through the bridge. It will go through the switch, which is not shown here, but then switch will connect to, for example, AP module, and AP module, CSI TX, will transfer the data to application processor. Application processor will work and do some processing work, and then the data will come back on the right-hand side, and then DSI RX will receive that data from application processor. It will go through the switch, and then switch will send that data to display module, and then DSI TX will send it to the display. So that's the simple data flow. Yesterday, you heard a lot of things about complexity of Unipro and how data transfer rate is very difficult, and what kind of information we need to worry about and all that. And that is what I think the purpose of this bridge chips and the switch chip is, to take that complexity away so that these chips will do all the work, and then module developer can live with the standard interfaces and don't need to worry about all these things. And then in the diagram, again, the dual case mode is also shown how the data is going to flow between them. So I know everybody wants to know when these chips are going to be available. Earlier, in the presentation, there was a question, or the panel, there was a question that we are using FPGA because it is not native, Unipro is not native. And the answer was given, but I think FPGA is being used for many reasons, but one of the reasons is because we need to have the development platform first while we are developing ASICs. So FPGA is being used right now on the development platform, but these ASICs will be available. And once these ASICs are available, of course, there is a different version of development platform will be available with these ASICs, and then that will be used. So everybody wants to use ASIC right now, but unfortunately, we have to still develop. So there is a high-level release milestone, which is here. This is for the developers. Of course, we are working closely with Google, and there'll be a little bit different schedule for internal schedule. But in couple of months, we will have white paper and product overview of this bridge chips. We will also have a website where we will release all the data sheets, which will be preliminary versions. And then, of course, engineering samples will be available in sometime in Q4. And then at that time, the more accurate data sheets will be available. And then after that, commercial use samples will be delivered. So that is the overview of the bridge chips. And then I think the more exciting thing about the open platform concept, which I was talking about, is this reference model idea. So we want to see if we can help the module developer community by providing or sharing the knowledge which we are going to gather during this process so that module developers' life can be a little bit simplified. So this diagram here shows that Google, for example, right now is releasing MDK to module developers. And Toshiba is developing bridge chips and switch for the Google. And this bridge chip, especially for the module developers, will be available from Toshiba. And then module developers will be able to use these bridge chips and the MDK and put their module together. And of course, we will provide all the support when the bridge chips are being used and all that. But I think more than that, what we want to do is, this is a traditional approach, but what we want to do is we also want to develop some reference models for the modules. And we are also ready to share the information about our reference models with the module developer. And that is what is kind of following the open platform idea. That is what I'm talking about. So just quickly wanted to show you our ideas on the reference models. So we are thinking of developing 3 reference models for the modules. One reference model is going to be for the camera. The second one is TransferJet. Maybe you don't know TransferJet, but it's a new standard to wirelessly transfer data at a very high speed. And then there is another idea here is to show activity meter type of reference model. So going back to camera reference model, what we plan to do is, for example, we have some technology within Toshiba, which is a computational array camera type of technology, or we have 13 megapixel high speed. High speed means 240 frames per second type of camera. We want to use this technology and then connect it with the AP bridge, make the module, and show user community how this type of commercially available technology can be taken, or you guys can take your own proprietary technology and embed that with our bridge chips and then connect it to the whole system. So, similarly, TransferJet, we have another technology, and then we can take that technology and connect with the GP bridge in this case, and then also activity meter type of thing with the GP bridge. So this is an idea of first camera prototype, which we are going to develop. This is going to be, again, using FPGA system. So this one, you can see that CSI3, which is a new standard, which is going to come after CSI2. And we are also developing FPGA to connect CSI3 type of standard with the Unipro. And that is one prototype which we are going to develop. And then here is the current version of the reference platform idea. So for example, we have two dual 5-megapixel cameras. And you can see on the right-hand side, those two cameras are in the module. And then on top of that, we have another product, which is a preprocessor chip. So we can put these two cameras and a preprocessor chip together and get the computational array camera functionality. Computational array camera functionality, once you have it, then you can do a lot of things with that. For example, you can do you can take the picture will capture a lot of information. So after picture is taken, you can focus on the front of the picture, and you can click on the back of the picture, and then that particular area of the picture will be focused. And so the refocusing can be done after the picture is taken, due to the computational array camera. We can also do depth map. So you can see over there, there is a grayscale picture of the same, or grayscale image of the same picture, where you can see what is in the front, what is in the back. Once this data is available, a lot of things can be done in the software. You can take the image, you can change the background, you can do the depth analysis, you can refocus, you can do gesture movements, all those type of things. So this technology is cool, but we can take that technology and, for example, take those two cameras, preprocessor, ISP, and then connect it with the AP bridge. And now that is the reference model for this module. And when we make this module, at the bottom you can see the module design image. And that module design image is, right now we are planning 20 millimeter by 40 millimeter size, which is in Ara grid 1x2 module. So that will fit in 1x2 module exactly. That PCB will be designed for that. The height, Z dimension wise also, it will follow Ara standard. So that will be the reference design. And then we can share this reference design, this type of idea, this PCB, this information with the user community, so they can probably come up with the more ideas. Here is another example, what I said earlier, 13 megapixel technology, what we have, which is very high-speed camera. Maybe you can you try to click on the video? And if we can play, yeah, there you go. So that little screen over there shows how that toy was flipping very fast, but you take one picture, but then that has a very high-speed camera, so we can capture 240 frames per second, and then you can play it in the slow motion, and it has a brightness features and all that. So again, with the same thing, we can go into module. At the bottom, it is shown that we can take that type of camera or image sensor, ISP, AP bridge, come up with the same 1x2 module reference design. The next one is a TransferJet new technology, which is a close proximity wireless technology. Again, if you can click on the URL, there was an embedded video, but maybe we can click on URL and see. So while it is playing, I can continue talking, but yeah, as you can see, TransferJet is the new technology which is to transfer data wirelessly between the two devices. The data rate is very high. It's 560 megabps. So you can take any two devices. One has a transmitter, the other one has a receiver, and then those devices will connect and transfer this data. So it is a close proximity transfer. So it's a 3 centimeter or less type of device. So basically touch type of technology. It is very secured. It does not go through long wireless distance, so people cannot intercept the data. It is ultra fast. You can take 100 megabyte video clip and transfer in few seconds. So this technology is the new technology, and then that technology can be embedded also. Maybe you can stop the video, but people can get the idea about that technology. So that technology we want to take and make a module. For example, here, what we are doing is that there is a coupler or antenna for transfer jet, and that is we can take that and then transfer jet receiver, put it together and connect with the GP module, and then again it will be in the module form factor, which is 1x2 type of module form factor. So again, our idea is to develop this type of reference module. And the last example here is about activity meter, for example. So we have a product for sensor hub controllers, and we have multiple axis sensor, like 9 axis sensors. So we can put all these information together and then connect with the GP bridge and come up with the activity meter type of module, for example. And that activity you are doing, what calories you are burning, all those type of things. And then, then the ideas can be limitless. You can take those modules and put it on your wristwatch and whatever you can do. So there are many ideas coming up, but I think what I wanted to show that our relationship with Google is going from inception of the standard to this chip development activities, and then as more forward, we are going to develop this module reference designs, and then we want to help the ecosystem of module developer. So I think just to help module developers, the main information is that we want to develop a portal, and this is a plan. We will have this portal up where probably in a quarter or so, and that portal will be open for all the module developers. They can log in to this, and they will have access to all of the work what we are doing, including the data sheets and both the bridge chips information, and also the module reference systems, and then the module reference schematics and Gerber files on a layout page and all those type of things you can download. And I guess that is my last slide. So we are very excited, and thank you very much.
All right. Thank you, Shardul. That's awesome. Fantastic.
Thank you.
All right, so we got a question on IRC. In reference to the close proximity wireless module, did you say the modules are different for senders and receivers, or are they the same module?
They're the same module. It's a transfer and receiver protocol they are used. Yeah.
Got it. And that is the only question we've got on IRC. So anyone in the audience, you guys have some questions for Toshiba about some of these reference modules? I see someone standing up. You going to the bathroom, or are you going to ask a question? All right, we have a question over here in the audience. Go ahead, sir.
Hey, could you talk a little bit more about the antenna for the module, the jet module, like how that fits into the...
Yeah. I think it's a lot of detail, but antenna, we have a transfer jet chip which comes with the antenna embedded in it. So I think we are really we are going to make life easier because it is kind of
Right, because that's
built
like
in.
6 gigahertz or something, right?
What is it?
It was at 6 gigahertz was the frequency
Yes,
of that?
yes, yeah.
Okay.
Yeah.
Thanks.
And we will give you more data if you want to understand more, but right now it is kind of embedded in it.
Thank you very much.
All right, let's go back to IRC. Can DSI Dual use bridge chips to support more than 2 displays or cameras?
DSI, we have 2 channels of DSI, so that can support 2 display right now, right? So I think we need more ports of DSI to support more than 2 displays.
Okay, good. And let's go back to the room here.
What package sizes are you guys targeting for the bridges?
Packet sizes.
Yeah, like as a component size.
Packet sizes.
Like what? How big is the part going to be? How big are the bridges going to be?
Oh, package.
Yeah.
Package size.
Yeah.
Oh, okay. I thought the data packet you were
no,
talking
sorry.
about. No, sorry. Package size. Package is, I put the TBD over there. We don't have the exact packet size, but it's going to be 0.4 millimeter ball pitch. So it's going to be small, but like the next version of the data sheets when we release in a couple of months, we will have a little bit more information in the package, but I don't have the exact package right now. We are working on the layout and information.
Okay.
But it's going to be 0.4 millimeter ball pitch, so you can kind of imagine.
Okay, and in the room, you, sir.
So the activity module that you showed, you actually had it removed from the phone and then put into a wristband in order to actually collect the data. That's going to necessitate connecting that module into the wristband in some way, which would you'd infer that there would be some kind of an endo there.
Yeah, so that is just an idea. There is no wristband or a watch which can have the same Ara module connector type of features right now. So as an idea, we are throwing, like I said earlier, that we believe that modular concept is going to go beyond smartphone, and these modules will go into maybe tablets or wristwatch, and that was just as a futuristic idea example.
We hope it's a current idea.
Okay, and still in the room, over here.
Yes, will the bridges be available as IP cores that we can put into custom ASICs?
Probably not. We are developing these products as a standard product, and it will be, if you see Toshiba, we have a lot of this type of bridges as a product, and our idea is to keep these bridges till the standard becomes native standard, like we were discussing earlier. So I don't think we are planning to release bridges as an IP core, which can be embedded into other ASICs at this point.
This is really more of a development bridge to the objective system. Then? Okay.
Yeah, I mean, we can think about it, but current plan is to have this as a silicon, the product. Yeah.
Okay, thanks.
This high-speed camera, pretty cool. Do you foresee any challenges with data rate and getting the data off that high-speed camera at HD?
There are always challenges, but I think we have high-speed cameras and we have HD cameras. We have image sensors which can handle this thing, so we don't see major issue. And DSI can take that data rate, and Unipro data rate is even faster. So there should not be.
Okay, thank you.
There should not be any specific challenge which is not there in the current system today.
All right, I think that's it. Shardul, thank you so much.
Thank you.
Appreciate it. All right. All right, folks. So we are a little bit early, but I think that's good. We'll have extra time for lunch here at the Computer History Museum. And those of you who are online, you can take a little nap if it's the middle of the night. and come back. So we're going to have another 4 hours of Ara Dev material happening in the afternoon. This is the end of my MC hosting facilitating duties. So I just really wanted to thank you all on behalf of the Ara team, Paul and David and Jason and Andrew and crew, and especially we had Ken Gabriel, who came yesterday to welcome you all, but also Regina Dugan, who is our kind of chief pirate of the Advanced Technologies group. She's actually traveling. She couldn't make it, but she's been following all the kind of the news and the buzz, and she's been in close communication with the team, and she wanted to make sure that you guys are aware that we're so excited that you're here, that you're asking questions, you're giving us feedback, because she believes and we believe that open wins over closed every time. And so anyway, just wanted to thank you all for coming. I actually wanted to do one small little thing before we wrapped up. Well, two things. Number one, for those of you online who are unable to get your questions answered, or for those in the room that are wondering the best ways to get a hold of us, Elwin is absolutely right. Please respect, especially NK Labs, Ara, and Seth and team. You'll find them on LinkedIn and other places, and you'll get business cards from them here. But we've got some great channels designed to give you guys feedback. The primary one is ara-dev@google.com. So ara-dev. And if you look in the MDK, there's a number of other kind of contact email addresses of how to get a hold of us. We also have a Google Groups that started up, so there's kind of a forum where you can start to engage with each other, and we hope the community will help to answer some questions. So we really encourage you guys to ask questions. The reason why we're here so early in the process is to get your input, your feedback, and to refine what we're all up to. Okay, so with that, we're going to close. I'm just going to do one last thing, and kind of in the spirit of Ellen DeGeneres' famous selfie, we may not get as many retweets, but what I'd like to do is encourage anyone who's online, who's been watching, even if you're in your pajamas, or you're bleary-eyed, or you're just kind of beat, if you want to, take a little selfie, tweet it out to hashtag AraDev, and we're going to do a little group selfie here as well. So I'm going to turn my little camera around, and we are going to do a little group selfie. So if you want to do a crazy face or hold your hands up on the count of 3, 1, 2, 3, AraDev! Woo! All right, that's super blurry. Thank you, guys. Awesome. All right, enjoy lunch. pass out some. Yeah, they've all been knifed. All right. All right. Welcome back to the second half of day 2 of the Ara Developers Conference. The next speaker we have for you is just amazing. I can't say enough about him, how awesome he is. He's super humble, too. So actually, my MC duties are done. The next speaker is me. And I'll talk about, a lot of people at the conference have been asking me, well, how did you get into ATAP? And what was your background? So I'll tell you a little bit about my story. And but before I get started, I'd like those of you who are like way in the back, unless you need an outlet for the moment, or in the sides, we're going to do actually some kind of hands-on activities with Play-Doh. If you're comfortable, feel free to come and fill the first kind of rows here in the middle. We're a little bit more intimate now because we have 3 different tracks going. For those of you online, if you can find some Play-Doh around the house, or just make some, just throw some water and flour, baking soda together. There's some online recipes. We're going to be using Play-Doh in a little bit. Okay, so let's get started. So I am known around ATAP as the design pirate. I was one of the first folks to come over from Motorola when Regina Dugan had first come to lead innovation after Google bought Motorola. And my job at ATAP, unlike the amazing brains of Paul Ermenko and Johnny Lee, who's doing Tango, and some of these guys who are just doing amazing technical innovation, my job has been to help all of the programs and projects across ATAP realize that at the end of the day, there's a human being on the other side of our innovations. And that human being has emotions. They've got experience, a life, and context. And so what I've been working on is both design research and some of the design philosophy to make sure that all of our projects and programs aren't just technically awesome, but that they really connect with people's hearts and with culture. I have a jar of Play-Doh on my head in most of my social media profile pictures, actually because it's one of the most awesome design tools that I've been using over the past 10 years. And you guys are going to use here too. And those at home that have made your homemade Play-Doh, you'll use it too. Okay, so this is Regina. As I had mentioned earlier, if you haven't seen her TED Talk about doing amazing things and reducing the fear of failure, well, how many of you actually watched it? Any of you guys take some time last night to watch it? All right, we got one. Nice. Awesome. For those that haven't seen it, it's a really good look into the kind of spirit that permeates our team. So Regina's our chief pirate. Now, what's really interesting about ATAP that was talked about by Ken earlier was that, like the DARPA model, we're not a research lab that tries to predict the future or tries to work on, the 15-year future of computing and engineering science, right? We make progress by making, by building, by doing in very short time periods. And for me, as a designer, this was actually the perfect environment for what I love, which is called co-creation or participatory design. And so what I want to talk to you guys today about, actually we're going to talk about what we've done with Ara Scouts, because our Ara Scouts have actually been the most visible example of this philosophy of co-creation. But half of this talk is actually about this way of thinking, and I want to equip all of you guys with some tools as you create your modules about how to engage with the people you're designing for. Okay, so many of you know that last summer we did this crazy thing called the Make with Moto tour when we were still Moto, and I wore my Make with Moto pants and my Make with Moto t-shirt because I haven't worn them in a year. And later on, we're actually going to give another session about what happened during that trip. But the reason we did Make with Moto was as soon as we had this idea about designing a phone that's really personal and that you're involved in the making of it, how it works, what it looks like. We said, what is the quickest way that we can prototype that? And so what we did was we took our existing Razer Max Moto phones, ripped off the backs, put on hackable microcontrollers into these guys. We used the yo-yo board that was done by Itai, this guy out of Google X. And we threw a lot of 3D printers on a truck. We got some guys here from 3D Systems they kind of had a bunch of heart attacks when we put some of their very expensive and printers that are supposed to be very stable on a 14,000-mile journey across the country. But we had a quick desire to prototype, right? Let's make some functional and aesthetic tools, and let's drive across the country and experiment. Q Techno, who's here, was with us in New York. How many of you guys actually were with us at Make with Moto? Can you raise your hands? All right, we've got a few. So you guys saw this at work. Now, as a designer, to me, this was the ultimate co-creation project because it gave us a chance to directly connect with the types of people that we're trying to work with. In many ways, going across the country at the nation's top universities and just ordinary kind of makers and just ordinary people gave us an early glimpse into the kind of things that you guys would care about. Like, how do we need to create this modular architecture? What are the kind of interfaces we need? All of that. Okay, so before I talk about Ara Scouts and what's happening there, I want to kind of share with you, we want to do a quick activity to talk about co-creation. So, most of you have used Play-Doh before. It's one of the most ubiquitous and popular and long-lasting toys in the world. And it was actually created early in the 1900s. But before it was Play-Doh, it was Kutal. Raise your hand if you know what Kutal is or have ever heard about Kutal. Okay, no one. Okay, so while I'm telling this story, if I can have a couple of volunteers take some of these jars of Play-Doh. I think I have a jar for every single person here. If not, just share with the friends. Play-Doh is really malleable. And I'm just going to tell you a little bit of the story about Kutal. So Kutal was actually created by, I forget the company that made this product, but they were this company that kind of had different abrasives and adhesives and things, and they were about to go out of business. And they were meeting with a large kind of store. And that store actually needed some wall cleaner. Because back in the early 1900s, a lot of American homes had coal-burning furnaces, and you would have, the effect of that is you would have soot that would gather on the walls. And so it was really important to have wall cleaner. And they asked these guys, do you have wall cleaner? We need 3 tons in a month. And they said, yes, we've got wall cleaner. They didn't have wall cleaner at all, of course. So they went back home, and out of the necessity of rapid innovation, right, to kind of deliver on this lie that they had, they quickly put together ingredients using flour and water and simple things, and they created a wall cleaner. And for years, Kutal was like this awesome wall cleaner that people would use, and they would scrub the soot off their walls. Now, you can imagine that the wall cleaning coal industry, was not the most sustainable, right? So as we switched to more different types of energy and heating, the need for wall cleaner started to decline. And this company was about to go out of business. But the wife of one of the founders was sharing a story kind of at this time about this classroom where she was a teacher. And because Kutal was kind of a fairly inert substance, they would use it, they would add dyes to it in her classroom, and her kids would use it as kind of an expression in their art class, a way to kind of sculpt and make and model stuff, and it would dry, and people would have these little sculptures. And much to the credit of the executive who heard about this story, he said, well, that is what we need to do. So Kutal became Play-Doh, and since that time, however many decades, it has been, again, like one of the most kind of ubiquitous kind of toys of creativity and play. Now, I tell you that story because it's an unintentional example of co-creation, right? This company creates a product, they have an intended use for it, but then they observe how it's really being used or how it could be used. They realize that that could be awesome, and then they create a much longer lasting sustainable business out of that. Now, there are ways that we can do this a lot more consciously, and I'm going to share some of those. And our Ara Scouts are an example of co-creation. Okay, so what I want you guys to do is take a look at this picture. This is a picture of a young girl brushing her teeth. And I'm going to give you an example from actually a fairly well-known innovation company called IDEO. How many of you guys have heard of IDEO? Okay, a lot of you guys. So IDEO is based in Palo Alto. They've got a number of different offices internationally now, and they're really well known for innovation and their process for innovation. And I've actually worked with IDEO several times. I actually love IDEO, but I think there's something beyond, just beyond the cutting edge of how they innovate that I think you guys should use around co-creation. So IDEO actually, many, many years ago, was asked by, I think it was Oral-B, to design a toothbrush for kids. Oral-B was trying to look at new markets and to design a toothbrush for kids. And at the time, this toothbrush that you see here, this general shape and form, every child's toothbrush was like this, right? Basically a shrunken down, smaller version of an adult toothbrush. Now, IDEO, from the start, Jane Fulton Surrey, who's their kind of head of, kind of human and, thought and psychology, has had this kind of whole vision around empathic design. So before we start laying down circuits or code or making a product, let's understand people. And the way to understand people is to go to them. So the IDEO team went out and they said, we're going to watch kids brushing their teeth. And Oral-B was kind of like, you're going to watch kids brushing their teeth? Like, how are you going to do that? Like, you have to go in their homes, get permission from their parents. And anyway, they worked out all the details, and they were able to observe kids in their native habitat brushing their teeth. And their sociologists and anthropologists and psychologists who were looking at these this activity noticed something pretty striking. So what do you guys notice about the photo here that might have stood out to you? Holding it higher up than expected. Okay, that might be one thing. Any other observations you think might be interesting? What's that? She's looking at herself. The brush head is way too big to get around into her mouth. Okay, how about how she's holding it? You have an observation back there? It's like her thumb's on the wrong side. Can you say it a little bit louder? It looks awkward for her. So, yeah, so when any of us adults brush our teeth, this is how we brush our teeth, with our fingertips, right? We have an architectural kind of grip because we have really good, motor skills. And so when we brush, especially when we get in the back corners, we're like really doing acrobatics with our fingers. But when kids brush their teeth, they have a completely different grip, right? They fat fist it like this because there aren't the fine motor skills yet, right? And so they observed kids brushing their teeth, and they were like, oh, there's this different grip. And they also noticed that with the small, kind of slender adult-style handle, that kind of toothbrushes were kind of rotating around and kind of flopping about. And so they told the designers this, and maybe even the designers were there, and they got inspired. And they went back to IDEO, and they took this kind of kid's bicycle that was in their shop, pulled off the rubber handle, popped in a toothbrush, and was like, that's it. And that was the first prototype. A few weeks, months later, they shipped something with Oral-B called the Squish Grip. You go into any place where toothbrushes are sold today for kids, every single one of them is fat-handled, right? Ergonomic. So my point to you guys is, it demonstrates the power of being in the world of the person whose experience you're trying to understand and innovate, and making careful observations about what's going on, right? If you had tried to do a focus group with kids, or the parents of kids, and say, what do you want from a toothbrush? They probably wouldn't have said, I want an ergonomically thick, squish handle, right? So this gets to the point that you need to have different methods to really understand experience. Now, what I want you guys to do is you have 60 seconds. I'm going to ask you guys to design your own toothbrush using Play-Doh. Okay, so get your Play-Doh out. Those that are at home, get your Play-Doh, or you can use bread if you need something that's easy to use. And we are going to have our 60-second timer, and I'm going to ask you all to make a toothbrush in 60 seconds. Be as innovative as you want. On your marks, get set, go. we have any Jeopardy music? Will we get sued by them if we use it? You can whistle it if you want. All right, we got 30 seconds left. Halfway done. That's right. You guys are all 3D printers, was the comment. All right, about 15 seconds left. Some of you are already done. Some of you are like, I'm not freaking doing this activity. I'm going to check my iPad. 5 seconds left. Okay. That's an awful sound. All right, we're done. Can you guys hold up your toothbrushes? I just want to see what we got here. Awesome. Awesome. Any particularly brave soul? I see a toothbrush hanging off an Ara phone. Any particularly brave souls want to kind of stand up and kind of just talk a little bit about what their toothbrush is? I don't know if we have a roving mic from back there. Maybe we can give somebody. Garrett, you want to go?
Ladies and gentlemen, this is the Ara 2014 Bluetooth-enabled toothbrush. It's got this wonderful ergonomic grip that fits in your hand, and it'll actually tell you what spots you're missing, what spots you might want to try a little harder to get, and it'll also tell you if you've got any diseases. We're using some of the same stuff that's in the space shuttle to tell whether or not you might be getting sick. So it's definitely should buy it.
Awesome. Awesome. Anyone else? Ash, you want to go? I'll just come on up real quick. We'll do one more. Anyone else want to come up to a mic? Yeah. What do you got there?
Hi, this is the first social toothbrush, and what happens is you can compete with your friends and have a leaderboard to see who can brush their teeth the best.
Awesome. Awesome. I was thinking of other scenarios with a social toothbrush that were scary, but that's good. All right, you got one too?
When I brush their teeth, they actually had something you put on the end of your finger,
Yeah.
and you actually brush, and I always thought that would be the greatest toothbrush.
Awesome. That's great. That's great. That's great. Well done. Thank you, guys. Now, for those that are online, we also want to see your innovative toothbrush design. So just tweet us at Ara Dev, and we're going to check those out later. Now, the reason why we did this is if the IDEO team that went out to observe kids and how they brush their teeth didn't have the best world-class researchers on their team and didn't make that insight about grip. But they had asked kids to actually, hey guys, I just saw how you kind of brush your teeth, and now what I want to do is kind of have you guys think about your ideal toothbrush, giving them Play-Doh or some other kind of creative tool like this and said, let's make some toothbrushes. They would have seen right in front of them these thick-handled brushes. And even for you guys, I saw it, right? Because it's easy. It's kind of what you naturally make in the hand. And those kids wouldn't have even known that that's what they were communicating, that I actually need a brush that's going to fit with my grip better. But it would have been painfully obvious to the team. And the IDEO team could not have missed that insight. Now, there's other things that came out. I've done this a few times now. I've seen toothbrushes where someone's like, well, actually, I'm done in just 30 seconds, and it's like a gumball. I want to brush my teeth like chewing candy, right? Like, how awesome would that be, right? Imagine getting your kids to brush their teeth if it's like a gumball every night. Or this finger thing, or the Ara toothbrush 2014, or social, right? Like, and all the stuff you guys didn't share, I'm sure there's pretty amazing things that you've kind of been able to express and explore in just a few seconds. So this, in its essence, is co-creation. It's about giving people tools that they feel comfortable with. If I had given you all AutoCAD, and I said, hey guys, I want you to kind of model something for me in 30 seconds, 60 seconds. Garrett would have loved that. He's like, yeah, done, right? But most of us who aren't familiar with that tool, would just like, I don't know what to do. I don't even know how this works, right? So the important thing here is you have to use a tool, a medium that everyone can relate to. So things like Play-Doh and crayons and Play-Doh, and I already said Play-Doh, Play-Doh again, and Sharpie markers, things that everyone can relate to are your friend. Okay, so we did the Make with Moto tour, which to us was, our tools were hackable phones, 3D printing, and actually in that case, us as human beings were the tools, the interface between what these folks wanted to do and helping them out. That process led to this. This is why you're all here, right? This is the Ara vision. This idea of this open platform and modular hardware came out of that. Now, when we launched, we knew that we wanted to keep a really close relationship with the people that we're creating for. So on the Make with Moto tour, we were meeting them in person. We connected with hundreds of people and had one-on-one conversations. But now that we were back in Silicon Valley, and we started to put a lot more emphasis into building out what you guys have seen over the last week, the MDK and all the kind of things in the program, we were feeling a bit disconnected. And we said, how can we keep an active connection with people? So I called up this guy over here, Michael Winnick. Michael, why don't you come up just for a second? So Michael Winnick is the CEO of a company called D-Scout. And Michael, we thank you so much for your help.
Thank you guys. It's been great.
So D-Scout typically had run research with 50, maybe 100 people at most, 150, something like that. And we said, well, okay, Michael, what would happen if we have hundreds of people simultaneously using your tool, maybe 1,000?
Right.
And Michael's like, oh, I think we can handle that.
Note that he called 2 days before this was supposed to happen.
I called 2 days before our launch.
Forewarning. So, yeah.
I called 2 days before, and they were like, let's try it out. Let's see. So we actually launched this web page, which, how many of you guys are actually Ara Scouts? Raise your hand. Wow. Awesome. Even our AV guys. No, that's Ash. Awesome. That's great. So what happened was, so this was a place where you could sign up to be a part of the program, and then everyone would automatically kind of get an invitation to download an app, either Android or iOS. And then later, we actually developed a web form for feature phone users. Now, we were overwhelmed. So Michael and I were on the phone that night. I think we launched at 8 p.m., Paul, something like that. And within the first 72 hours, these are the snippets that were submitted. Now, a snippet, just so we have a clear sense of terms, is a piece of content that an Ara Scout, one of these individuals, contributes. And it could be an idea, something about their life. In this case, this was called, I think, First Impressions.
Yeah.
And I think it was that night we quickly realized that D-Scout servers were just going to explode. And we had to call the CTO, get him out of bed. They had to kind of do some quick Amazon cluster reshuffling. Do you want to talk just a minute about what happened on your end?
Yeah, it was kind of like a traffic tsunami, is the only way I could describe it. Our chart just looked like, it wasn't even a hockey stick, it was just a straight line and then a wall. So it was a fun challenge to try to, I think it took us 3 or 4 days to recover, changing server hosting environments, things like that. But I think we mostly got through it somewhat intact, right?
Somewhat,
okay.
Somewhat.
Yeah.
Well, thank you, Michael.
Yes, thank you.
So Michael is actually going to be around later on today. And actually, D-Scout is a pretty interesting tool that for module makers that want a really quick and rapid way to connect with the people that you're designing for and kind of understand things about your life. It's a really good way to kind of get that connection, because you can imagine, what if our team tried to go like IDEO and visit kids brushing their teeth and actually try to visit all these places? Like, there's no way, right? Through travel and all of that, we'd be able to do that. So D-Scout is what's called a self-ethnography tool. Right? Ethnography is the study of people. This is what anthropologists and sociologists are trained to do. But what's cool about self-ethnography, it's where you're able to kind of talk about your own life, and you're able to kind of share what you're excited about. Now, very quickly, we saw stuff like this. Like, not only were people kind of taking pictures or downloading pictures of like cats, and like that because they saw our cat on the launch, and then they were just, all kinds of Ara memes were generated within that first day or two. But then people were like drawing their own artwork. And I thought this was particularly appropriate, where Ara is the phone that opens the door for the future. So people were kind of just getting excited and sharing that excitement with us. And we were overwhelmed. Now, what we did is we made this picture. This is the same picture you saw before, but instead it's made up of little tiles. Because we're a modular phone, this is a modular picture. These are the first Ara Scouts that we had in that first week. These are their profile pictures that they submitted to us. Which to us is a good representation and metaphor for how we feel. We feel that these scouts are a part of the team. We can't always hang out with them in the hallways and have Google lunch with them, but we can, we can connect with them and we can invite them into the process of making and designing. So since we started, we've actually done 5 missions. We're actually launching our 6th one right after the conference. If those of you who didn't raise your hand want to be an Ara Scout, it's open to anyone at any time. So you go to dscout.com/Ara to sign up. For those of you who are online, I'm sure many of you are also Ara Scouts, and you can invite your friends. Now, let me just give some terminology. So a scout is a person, right? It's a person who we feel is like an extension of our team. A mission is a really small task that we ask our scouts to do. And that mission can be any number of things. But the best mission is not just a simple question. Like, a good mission for, in the example with the toothbrush and the kid, is not, what kind of toothbrush do you want? It's, take a picture of, like, the most awesome thing and the most frustrating thing when you're brushing your teeth. And tell us about it, right? So you want to connect with people where they have an opportunity to share something about their life without you constraining it too much. So we've now done a few of these, and I'm going to share some of the results of these. But first, I'm going to continue a little bit more about this open design research and co-creation. We'll talk about kind of 10 things that came out of these first 5 or 6 missions that we've done. And then I'm actually going to announce the most active scouts. So some of you may be asking, why are people doing this? Are they just fans? Well, we're also incenting them, right? So we've said that the 100 of the most active scouts will be the first to get an Ara phone outside of our team. And so just like Ash yesterday and Kyle online, we're going to actually have 102 people now. So Ara scouts will be the first 100, and then those 2 folks from yesterday are going to be the first ones to get an Ara phone before it's ready for the available the general public. And we've looked across all the people that have participated, and 17 of them have emerged as folks that we're ready to say that they're already part of that first 100. And then we'll have some time for Q&A. Okay, so let me just start by telling you just a story. Back in the day when I was at the beginning of my career, I was working for a hot consulting company called Studio Archetype, which was later bought by Sapient. But we were doing cool stuff on the web. Before Ajax was a term, we were doing like dynamic stuff. And we were doing the website for United Airlines. Super huge transactional sites with tens of thousands of pages and interactions, right? And I was one of the design leads. And I had done a lot of design work in the web space and kind of was, ready to tackle this challenge as an information architect. The week before, we had just brought on a couple of folks who were called design researchers, and I had no idea what they were. But they did this thing where they brought in about a dozen people, and over the period of a few days, did this thing called paper prototyping. And it's Post-it notes and markers, and they had kind of, had this home page, and they said, look, just imagine this is a web page, use your finger to click, and I'm going to ask you some scenarios. And what was really cool is that they actually had some markers out and blank Post-it notes out. And so if someone was kind of going through this like paper version of the early thoughts, what the team thought the website should be, how it should be organized, how sections should be named, and the nomenclature, if that wasn't working for someone, someone said, well, I want you to find out status on a flight, and no one was like finding the place where that team had thought that should be buried. They said, well, listen, just make it. So well, that should be called flight status, and it should be right at the top, right? Or so they could draw on these pieces of paper. And at the time, I was like, what the hell? Like, our client is paying us in excess of $300 an hour per person. And we're like using Post-its and paper and crayons? Like, come on, guys. Like, we can't tell the client. Does the client know we're doing this? Like, I was really embarrassed. But by the end of this process and sitting in these sessions, and actually then sitting with the rest of the project and seeing it unfold and develop, I saw that the insights that were developed using this very simple medium, this team had solved the top most challenging interaction design problems and challenges that on other projects, it was just, our smart team would solve using whiteboard sessions and discussions, and we'd usually get it wrong, and then we'd do a prototype using a lot of code, and then we'd still get it wrong, and then we'd try to fix it. But they had done it even before we started laying down lines of code. They had gotten these insights, right? So I was blown away. My skepticism and embarrassment turned to rabid excitement, and I said, where did this come from? Did you guys make this up? Is there more of this? Where did that come from, right? So through my research, they introduced me to this lady who, in the striped shirt here, this is Dr. Elizabeth Sanders, or Liz Sanders. If you want to know more about Liz Sanders, a good way to look at her is maketools.com. Maketools.com. She is my hero. Of all the people in the world, of all the greatest designers and innovators, Regina, I love you too, but Liz is really my hero because she's really influenced the way I think about stuff. And what she has done is she's been the thought leader around co-creation. This is an example of someone on her team in the top in the white shirt is working with these two nurses. And what they're doing is they're kind of exploring what a future hospital wing should look like. Right? There's a team of architects and engineers kind of building out this new hospital expansion. But Liz and her team were hired to kind of really understand the people that are going to use that space, what are they going to do? And look at the tools, right? The tools are scissors, there's adjectives and words, there's kind of poster board, there's markers, there's kind of circles, and they're looking at kind of the flow of information and stuff and kind of where it's broken today and what could happen in the future. And she felt that this whole UX thing, user experience, said there's no such thing as experience design. She says that experiencing is in people. That an experience is a moment in time at the nexus of our kind of memories of the past and our dreams of the future, and no one can design that. We can barely understand our own experiences. You know, some of you that have come here, it'll be months, maybe a year later, you'll look back on this moment at the Ara conference and you'll say, oh, that's what that was all about. That was a real meaning, right? We have to blog and journal and Instagram and take selfies and kind of, try to capture our moments so that we can look back on them and we'll have different views. So if we can barely understand our own experience, how can we presume and be so egotistical to think that we can design someone else's? But what Liz said is you can design for experience. And if you notice here, the future is the key part. We're all makers of the future, right? The stuff that we're creating and making does not yet exist, but we have confidence it does. It will, right, technically. But what about people? What about the people you're creating for? What about their dreams? How can you access those? And this is what Liz worked on. This is another example of Liz's early work. This is a Velcro modeling toolkit. I'm not sure this inspired the Velcro on our Make with Moto van, but this is one of the early innovative uses of Velcro. On the left, you see these gray shapes. And on the tray there, you see all these little kind of beads and buttons and things. And there's Velcro on the bottom of those. And so those can be stuck to all of these shapes. And so on the right-hand side, it's a father and a son in their living room. This is actually a project for Microsoft, where they're designing a game controller, a Sidewinder controller for PC games. And these guys have these tools, right? So this is kind of like another version of Play-Doh, where they can start to choose a shape that they like, kind of take different controls, and use it as a prop to tell stories about what they want from the future. Now, I'm going to have a few more slides, and then I'll show you what we've done with DScout, what we've seen there. Okay, so according to Liz, and this is straight from Liz Sanders from Make Tools, some of her papers, there are only 3 ways to understand people. If you want to understand people you're designing for, you can listen to what they say. This is 90% of traditional market research. It's surveys, it's interviews, it's focus groups, it's one-on-ones, it's all of that. And that's good. But like I said earlier with the toothbrush example, what people say often differs from what they do. Right? If I asked you to describe, how do you drive a car? Right, you'll think, well, I don't really think about it. It's kind of automatic. But what I think I do is I kind of do this thing and I do that. Now, if I actually watch what you do, that's the do part. So I can actually sit next to you and I can watch what you do when you drive. And I can notice that, oh, you actually sometimes drive with your knee when you're checking texts on the roads. You didn't tell me that earlier, right? That's kind of important. You broke the law. And this area of do has been the most innovative place in design research over the past several decades. It's sociologists and anthropologists and psychologists coming together with designers and engineers to help understand human beings, right, and what they actually do. Now, the third part is what they make. And this is what I've been showing with you today. Now, according to Liz, and this is debatable, but to me it's very true in my experience, is that on the right-hand side is the kind of knowledge that we have as people, right? There's the explicit knowledge that we have that we can just, is very on the top of our heads and we can talk about. Then there's kind of observable knowledge, stuff that I might not be super aware of, but if you observe what I do, my patterns, you'll know it. All the way down to latent knowledge, right? Tacit and latent knowledge. That's the stuff that I have. It's information I know about, but it's so deep and maybe so profound and so important. This is the stuff that you work with therapists with, like father issues and like the deep stuff, right? Now, there's not just the negative side of the deep stuff, but there's the positive side of the deep stuff, like your dreams, your hopes, right? If I asked you, what's your dream? What's your hope? Like you might kind of stumble a little bit to kind of bring that to explicit knowledge and tell me, right? But there's something there, right, that helps to motivate what you do. If you want to know that knowledge, and that's where the good stuff is, you have to use tools and techniques to get to that. And that comes out when people make. When people make things, you see things that they may not even be able to express in words, right? This is kind of like a picture's worth 1,000 words, right? Well, someone's creation is worth many, many pictures, right? There's so much richness in what people create. And that's where what people know, feel, and dream. I'm going to skip this slide so we can have more Q&A, but essentially there's this wide range of tools in the design research landscape. I encourage you to use all of them. But I just want you to know that we are most comfortable as an industry and as a community in the lower left-hand side. This is a place where it's much more led with a research mentality, and it's where we think about the people that we're designing, with or for as subjects. We don't really treat them as rats going through a maze, not like that bad. But sometimes, like I don't know if any of you guys ever go to a usability study at, somewhere, like depending on the facilitator, you kind of feel like, well, you're not telling me what you're doing, and you're paying me $20 at the end, and I'm not really, you kind of feel like you're going through this weird kind of maze, right? But there's really valuable stuff in there. Usability and ergonomics, and there's a lot of greatness there. I'm most interested in the upper right-hand corner because it's the most unexplored. This is where it's more of a design-led, meaning that people can actually create stuff, not just test the stuff that you've already made. And most importantly, and if you remember one thing from this talk, this is it. People are not users. It's actually a pretty offensive term when you think about it. There's only 3 industries that use the word users to describe the people that drive their stuff. Drug use. I'm a user, right? Prostitution. And for some reason, technology, software and kind of design. People are not users. People are human beings with a rich set of needs, emotions, dreams, and hopes. And when we treat them like that, and we recognize the reality, very different types of methods emerge, and that's what we've been trying to do with D-Scout and with our Ara Scouts, is try to invite them into the process, and they're helping us actually create things. Now, it's a different model of designing and engineering. The classical model on the left is you have this you as a user, an R as a researcher, a D as a designer, or an engineer for you guys, and a researcher goes out or reads some report and kind of hands that off to a designer. They try to make some innovation, and then they test it out later, right? That's the current kind of model. The model on the right is a more co-creative model where everyone's kind of sitting around the table. You got engineers and designers, people, not even users, but people. And using some new tools, they're able to explore different types of scenarios, right? And D-Scout's one of those tools. Okay, so now, part 2 of the talk is what have we learned? Now, quite honestly, we've gone through a debate on our team about how much of the photographs and videos and richness that we've seen as a team come out from our Ara Scouts that we should share with you guys. And while I think that most of the Ara Scouts that are here and online and would see this presentation later would be super psyched to see their idea or their phone prototype or their face like live to the world, we know that there's some people that wouldn't want that to happen. So I'm just going to give you an early apology that we've tried to give you as much of that direct kind of inspiration that we've seen, but we've decided not to show people's faces and not to show their homes and lives out of respect for the relationships that we have with our scouts. So, but here's some examples from Mission 3 where we asked scouts around the world to make a phone. And again, we had people make stuff, and the stuff that they made was amazing. And the ways that they attached their cardboard modules to the backs of their prototypes, the kind of modules that they chose in the first place, the way that they kind of made the aesthetics was just, I can't tell you how awesome it was for us as a team to look through this. Now, before I go and share with you a couple of the things that we're seeing from Ara Scouts, I want to give you some of the numbers. So we've had over 78,000 people sign up on dscout.com/Ara. We've had about almost close to 30,000, maybe I think it's probably 28,000 or so folks have participated in at least one of our missions. We've had over 2.25 million words submitted to us across all missions. That's more than 56 novels. We actually had to hire 2 PhD sociologists and anthropologists to help us digest and read those 56 novels. Like those that are just learning about Ara now, they're not some of the early geeks that were like, yeah, Ara, October 29th, I was the first to know. But like the folks that are learning now kind of maybe represent another group of folks that we also want their perspective to be heard as well. Okay, so here are the words that people use to describe themselves. We had a mission called Getting to Know You. And you know, this is self-ethnography, right? So if I asked you, what are 3 words to describe yourself? You may say, I'm handsome, and I'm intelligent, and I'm awesome, right? So, but there is some honesty here, right? You see that there's lazy, and shy, and quiet, and tech, and crazy, and geek. But I think when you look at these words, it's actually a pretty good reflection of the kind of folks that are part of this community. We really have everybody, so it's not monolithic by any means. The 2 words that I thought were really interesting is curious and creative. So we believe that our Ara Scouts, who we believe will be the first champions and owners of Ara phones, are folks that are like really, they're curious, they're creative, they're interested in tech, they're geeks, they're ready to kind of work with us as we demonstrate the power of what this platform could be, right? They're kind of a little more early adopter folks. And this is, and to show how they're creative, this is some of the fan art that we're seeing coming in the first mission. So we're seeing all kinds of really interesting kind of ideas around kind of how this thing, you know, could look and feel, and like, you know, and the other thing is the largest group demographically, age-wise, are folks in their 20s. The second largest group are folks in their teens. So Qtechno, you're probably representing who's 13, but you know, well older in his knowledge and wisdom. And we kind of have a cutoff on most kind of networks. I think you have to be 13, right, to kind of use apps like this. And I don't know if we have a cutoff, Michael. We do, 13. So teenagers might actually be the largest group if we went all the way down to 10. Now, what I really like about this slide is at the top it says it's the phone built for anyone and everyone. What's really exciting here is that you'd think that with a phone that's infinitely configurable, and I can make exactly what I want, that there'd be a lot of narcissism and kind of real ego and kind of self-focus with this group. But we see time and time and again in the contributions from our Ara Scouts that what might be even more motivating than the desire to get something that's perfect for me is the excitement to be a part of this platform and this movement and this phone where I know that other people can also get what they want, right? And a lot of people get excited about the eco-sustainability implications of that. They get excited about, you know, knowing people who like, I want a smartphone, but I really want a physical keyboard. I can't get that today. What am I, you know, like, so I think it's really important to note that there's a lot less selfishness than you would think with the first champions of Project Ara. Okay, this slide's a little weird, but it's my desire to get beyond boring graphs, because I got a lot of boring graphs coming to you. But this is like, imagine that each one of these things represents 10%. So that's 100% of our folks. In terms of software, we have 70%, so 70 people are using Android. And that's kind of expected, right? This kind of came out of Motorola at the time, and is now a Google project, and our Android is our top target. So most of the folks are Android. Now the bottom, you see those two little Android guys on the left with the Apple logo cut out of them. We have actually 20% folks using Apple, and actually Apple devices, so iOS. And at the beginning, it was actually a little bit larger than that. And that was shocking to us. That was shocking to us, right? Because, you'd think that with this whole kind of Android, iOS fanboydom kind of craziness that happens, that honestly we don't care that much about in terms of the politics of it. But there was kind of an expectation that this is going to be an Android community, but it's not, right? There's all kinds of people, and a whole quarter, almost a quarter, in this case a fifth. In some of the early missions it was more. That's kind of exciting. Now we only have 10% other. I think there's 2 people using BlackBerries, maybe 4 using Windows phones. No, it's more than that. But most of those are feature phone owners. And what DScout has done at our request has created a web-based way for people who have access to the internet, which represents really the majority of the world's population, right? They don't have smartphones today. They're not able to use an app on iOS or Android so that they can participate. That number now is 10%. We're hoping that that can be a lot more. So if any of you guys, online or in room, know of people that don't own smartphones, we would love for you to invite them to participate with us. Because that's a really important perspective, especially as you'll hear in the next talk about how we design really for the next 5 or 6 billion and have a global perspective. The other thing is we've ranged from 2% to 15% female. So we have the 2 female androids up there. I don't know if that's, they're kind of a cross, but this is a very testosterone kind of place. And again, we really want this to be open to everyone, but we kind of recognize that it seems to be, and if you look around the conference here today, that this is a very kind of male, dominated place of interest. This somewhat follows other kind of early adopter trends, but we really want to make an explicit call out there that this really needs to be balanced. And we really need to have different perspectives. And part of the reason why co-creation is important to all of you is in the early days, your teams may be unbalanced, right? You may not have enough perspectives. We really, really want to give you guys tools to make sure that you're being inclusive and making sure you're designing modules for the world. Okay, a couple quick data points. For our largest mission, where we had something like 17,000 active scouts, we categorized all of the chatter and snippets and discussion against these categories. Most of the discussion was around just kind of, oh my God, it's modular and we can make stuff. Some of it was around, if I can make stuff, it can be just mine. I can customize. I can do whatever I want. And then there's some that were just like pure excitement. We had so many like OMGs and like shut up and take my money. And like we had like thousands of memes from people, right? Just pure like, oh my God, I can't believe this is happening. And part of that is because just a couple months earlier, Dave Hackins had shown phone blocks. And then a few months after that, Reddit had said that's impossible. And then we were like, we're actually doing it. And people were like, oh my God, right? So part of that was because of that dynamic. But what's interesting here was, and there were concerns and questions and all of that, many of which drove some of our thinking around things that we thought that you'll see in the MDK, some of the technical innovations on how does this stay together? What about water? All that kind of stuff. But if you look at the fourth area, this is sharing. This is not something we expected. We kind of had this idea that, well, if you have a modular phone, you can swap modules. Like we kind of thought that might be cool, but a lot of people found that to be really cool. Like we would have families taking pictures of like all the phones that they had in the family, of like 5 or 6 phones, and they'd say, we all have to get all this stuff, but like what if we spent like $200 on like an awesome camera module, and then, and we could share that among the team, among the family when we were going on vacation or something, or other scenarios like that. And we were kind of excited about that. So as you guys are doing modules, think about those kind of more social kind of aspects of the technology. Here's a couple of just snippets that we got back. This was, I'll let you read this quote, but this is kind of this idea about customizability and the excitement. And then it's this thank you. Thank you for leading the way and connecting with a like-minded community to get this project in locomotion. We wish we could actually write back to every single person those 2.25 million words that have come out. We can't quite do that. But so I want to tell all of our scouts now, we've seen everything you've given us. And we've been inspired by it all. And we're really thankful that you're participating with us. A couple other examples. This is an example of that sharing scenario, right? So people are showing sketches, and you just get the idea, right away from these real simple pencil drawings and marker drawings. And then the last thing that we saw early on was this desire to be part of a movement, right? We call this Moto and Me. Now it's Google and Me or Ara and Me, right? The fact that people get to participate in a project like this so early on is pretty unprecedented. I can't really think of another project kind of at this scale where the company actively invited people to be a part of the process. And people get excited by that. And we get excited by that as well. And hopefully you're excited and you're here because of that, right? Okay, some more stuff. Take a look at this. And maybe a picture of this, and someone can blog about this. This was in the very first couple of missions. We counted out the number of mentions of particular modules. So this is what's on the mind of our Ara Scouts. Now, our Ara Scouts, again, I showed you I talked about the demographics. It's not quite the majority of folks, right? This is kind of your early adopter crew. But these are the kind of modules they're talking about and asking for. Cameras, if any of you guys are in cameras or know people that are doing camera stuff, camera is by far and consistently the most desired kind of scenario and piece of hardware. If you can do anything around cameras, I think it'll be really awesome. And I hope we have a lot of really good camera scenarios. And then the usual things of battery, screen. Calculator came up, which is super weird, right? That was like the number 4. But again, when you think about a lot of these folks are students, it's kind of an object that's around that's like, oh, I could calculator, right? Hopefully that's not for cheating purposes. Okay, and then there's gaming stuff, there's music, and there's a whole list of things, right? So, and we kind of like scenarios like car keys, right? Take stuff that I have to carry around with me all the time. What if I can integrate that with my phone, right? And have that help me, be the keyless entry to my car. Medical stuff, robots, scanners. So anyway, this is some of the early stuff that we saw. Now, later on, when we did Mission 3, we asked people to build their own phones. We asked them to kind of pay attention to what modules they would want to do. This is when you ask people what they think, what they say. This is what people actually make. When we analyze kind of the percentage of scouts that use different modules, I guess none of these are really, surprising. You'd expect all of these to be there. But you can see things like USB and more storage kind of being separated a bit. So I don't know if USB exactly what that means, whether that means portable storage like drives, or whether that means I want a module or something that'll help me connect into the other world of modular peripherals like USB or PCs. But that was kind of interesting. And then here are some of the more interesting modules that we saw by frequency. So NFC surprised us. Like, really? Like, most people on our team hardly heard of NFC just a few years ago, right? So this is a very educated group, right? The fact that NFC is mentioned so frequently. Okay, we got a couple more. Now, just to show you that we're not just looking for qualitative, subjective kind of, I'm excited about Ara to make ourselves feel better about the project. When we had people make their phones, we said, we want you to make it the perfect size for you, especially width and height. So put down your current phone, draw an outline on a piece of paper, and then think about kind of whether you want your ideal Ara phone to be bigger or smaller, cut it out onto cardboard, cut out another piece of cardboard, cut that up into modules, and glue everything together. So that was kind of for Mission 3, that's how it worked. And we asked people to send us their dimensions, like what was the size of your phone? So I love some of these these dots out here in the far right and left, because I mean that would be awesome. Like I know phablets are like cool these days, but that would be like you'd be carrying around a display. It may have been we misinterpreted millimeters for inches. I mean I don't know, but you can see where the massive dots was landing, and those green X's are actually the 3 sizes of our endo skeletons. So we've made a very conscious decision for those 3 sizes to find a range that we thought would meet kind of where folks are really interested in. And actually, you can see the large frame is, fairly well outside of the mass of folks that want a bigger phone. So it really gives a good option. Maybe not this person all the way to the right. They won't be happy, but they'll be happier, right? So very specific engineering things like size were really well informed by what our Ara Scouts contributed. Okay, our last mission, which was super awesome because our Ara Scouts found someone who doesn't own a smartphone and configured a phone with them. And a lot of our scouts sent us messages like, I can't find anyone who doesn't have a smartphone. But when they did, the folks that they were interacting with had just the most awesome questions, like, why would I want a modular phone? Like, what is Ara? Just who cares, right? I just want my phone to work. And so it was really humbling for us because the kind of questions and excitements and concerns that came out of that really make us think differently about how to do the UI, how to help people make a phone and all of that. So these were the questions that people asked their friends as they were making a phone. And cost was huge, right? A lot of people don't have smartphones, not because they don't want a smartphone, but because, it costs a lot for a friggin' data plan and for that phone and all of that, right? So, and then there are all this kind of long tail of questions. But what was really fascinating was we also categorized the things that were most exciting to people. So the next one was actually the same things that were the questions, like modular phone, WTF, became modular phone. That's awesome, right? As soon as people understood how this could affect their lives, like, hey, I can swap a battery out at the end of the day and it's a fresh phone. Like, that's awesome, right? Or I drop my, people would try to customize with folks and their screens were all cracked. They said, well, you can just swap out a new screen super easily, right? People got excited about that. And the process itself. So when you guys think about making your modules, you have to train people and teach people and kind of welcome people into this process of how to use your module and what it should be, right? And we have this whole process where the owner of the phone is going to be able to design the outside of that module, what it looks like and feels like, right? So really welcome people into that process. Don't leave them alone and say, you just figure it out. Give them some good guidance. But the things that are exciting are also the challenges. So the Ara team is working very hard to make sure that we meet these kind of concerns. Okay, last thing, and sorry I'm not leaving a ton of time for questions, but we'll have a time for a couple of questions here. So from the beginning, we've said that 100 of the most active scouts will receive the first version of the Ara phone. We don't know exactly when that will be. We don't know exactly if that's going to be part of a beta or dog fooding program. But as soon as we have kind of, a ready, stable version of Ara phones that can go out, our Ara Scouts plus the 2 folks from yesterday are going to get those phones. And we're going to ask them if they'd be willing to kind of really give us some of the early feedback and kind of go through the customization process. So like I said, we have yet to choose the whole group, but there were 17 of them that stood out to us as being the most active. And so these 17, this is the first time that we've ever shared this list of people. We will be notifying these people within the next 24 hours so they're aware. So if those who are looking online and like, holy shit, I'm one of those people, we're going to reach out to you and tell you what's next. Do we have any of these people here in the room? Okay. Now, there are those of you who have been with us kind of from the beginning and like, well, why am I not on that list? And there were actually, after these 17, there was a whole group of folks that has really been thoughtful and really been consistent in contributing stuff onto D-Scout. So don't worry, don't give up, continue on. We have another 83 spots left. We'll be choosing those after another 5 or 6 months of missions. At the beginning, we said we'd be doing 6 to 12 months. Now that we have a better understanding of the time frame and our need for continuous design research, we'll be going for about another 2 Ara Dev conferences. So we want you guys to continue on. If you've never participated before, you're welcome to join. People have asked us, well, what's an algorithm? How can I be the most active scout? And we say, we actually do have an algorithm because we have some Google data scientists and they love this kind of stuff. But the things I can say is quality and consistency. So if you're going to participate with us, make sure that you do those 2 things. All right, guys, that's it. Let me take a couple of questions from the audience, and then I'm going to turn it over to the next talk. Any questions? Just come up to the mics here.
So what is something that you thought you knew about the Ara project that the scouts made you rethink that it was something that you thought you knew that you realized it was different?
Yeah, it's a good question. There's many, many things. I think one thing is we get really excited about the technical possibilities of the program to kind of reshape choice in the industry and personally. We talk a lot about this is, the first phone exclusively designed for 6 billion people. We get excited about that. And we've realized that most people don't actually care about those things as much as we do, right? What they really, they'll ask the question, why should I care, right? And there's actually many different reasons why people care, but they're not the ones that we had thought of. A lot of people do care about the fact that I have just more choice and I can have a phone over a longer period of time. There's super geeks that are like, oh my God, this new 64-bit processor is going to come out and I can just swap it in and just pay $50 or whatever. They get excited about always being the sharp tippy point of nerddom. And then there's a lot of people that really like that modularity because they can get what they want. We've had people, the best one ever was we had someone put a rotary dialer on their phone as a module. Because that's how they like to dial numbers. And they haven't gotten a phone yet because it doesn't work how they want it. So if any of you guys want to create a rotary dial module for the front, awesome. All right, I think we have time for one more question, and then we're going to switch over.
Hi, thanks. Steve Anglin with A-Press. One question I have is, beyond the hardware and the firmware modularity, what about software, an SDK of sorts, or, what are your thoughts along those lines? Obviously, you can't detail anything that's in the works now, but what would you like to see in terms of a SDK to build software, more modular software for this kind of phone? Thanks.
Yeah, no, it's a great question. It's a little bit outside of my area of expertise. I would encourage you to go to some of the MDK feedback sessions in the other room that are especially Seth Newberg specifically, because I think he'd have a really good technical answer. I think we already recognize there's a lot of tools and excitement and energy around the Android SDK space, and we feel like we want to make sure that all of that energy and enthusiasm doesn't get squashed and squandered with Ara. Whether or not we want to create something, a new set of tools or something, I don't know, but everyone that I know has an idea for a cool app, and a lot of them don't have the skills to make it or code it. So just in general, my personal Daniel McCoskey comment, not as Google or Ara, is that it would be awesome if the app software space can be more like a co-creation space, where someone who has got an idea has a way to easily, rapidly prototype that. Yeah, cool. And on the Make with Moto tour, we actually hired a coder to help make an easy prototyping tool called Protocoder. He couldn't make it here, but so I think that's a cool space. All right, guys, thanks so much. Appreciate your time. Do you want to? I'm going to give him mine. You got to turn it on.
This is on?
Yeah. Let's just do this real quick. Okay. All right.
Okay. Good afternoon. My name is Jose Gomez Marquez, and I direct the Little Devices Lab at MIT. And I'm really excited to be here. Now, what we get excited about in the lab, we basically create affordable medical technologies for health everywhere. But our focus is really not just on creating the end devices. We try to create interactive spaces and construction kits so that lots of people can make their own devices. So when I get a call from Nicaragua, or one of our researchers gets a call from Nicaragua and says, we've made a different type of nebulizer, that's what gets us going to figure out, okay, what types of tools could we design so that they can make the next one? And how would they make a spirometer? How would they make an inhaler? And then lots of other things. Because for us, if healthcare is going to become accessible and democratized, we really believe that you should be able to do it yourself. So when Paul called a couple of weeks ago and said, hey, we have this project, I said, yeah, I've read the articles, but that's as much as I know. And they wanted to look at, what types of health technologies are out there, what types of health problems and challenges are out there that could potentially be solved or addressed by unleashing Ara modules. Of course, if I had a whiteboard during the conversation, we would have filled it in about 30 seconds. But effectively, it was really encouraging to know that there was another group that was very much aligned in that same approach of saying, how do we just open up the space, and specifically in health, so that everybody can play? Because that's what we're all about. And I think if you like that approach, if you think that health is open and should be accessible, we would love to work with you. And let me show you how we do this. Of course, one of the immediate things that happened as things got tweeted and the agenda got published that we saw was that a lot of people said, okay, MIT is going to unleash the tricorder. And so let's talk a little bit about the tricorder. One of the things that we realized is the tricorder is this fantastical device, last used by Dr. McCoy, maybe in 65, 60, I don't know. But that can just scan us. It can tell us what's wrong with us in a few seconds. But one of the things that we noticed is that it's really a one-size-fits-all. And in healthcare is a very diverse system. We have lots of diseases. We have lots of people. We have lots of geographies. So one-size-fits-all is really kind of a recipe for disaster, we think. It's disaster and disparity. Our vision in the lab, and I think it's very aligned with the folks in this room, is how do we create 1 million tricorders that are all reconfigurable, that are made up of a bunch of devices based on what's around in people's backyard, instead of one monolithic thing basically trying to solve another monolithic thing like health, and just kind of one monolith chipping away at the other. We're just simply not going to get there. And so instead of trying to design this like black helicopter of medical technology, or for those of you who saw the Lego movie, the craggled version of a device that's only able to be made by the master builders, how do we make the universal Lego set for health? So I'll show you some stuff that I think that is hopefully leading there, but we can't be the only game in town. Part of the problem and why we got to where health technology is, which is largely black box design, is that in science and technology, we have this vision of magic. Arthur C. Clarke said that any sufficiently advanced technology is indistinguishable from magic. And so that for us is often the standard and the baseline, that awe moment that we want to create. But my problem with magic is that it's a black box. It's mysterious. It's not necessarily accessible or transparent. And if you want to design for the next 6 billion people, you have to push for transparency in your approach. And in medicine and in wellness and in health, we are filled with black boxes. They happen to be white in most cases, but when you walk into the doctor's office, you basically find lots of devices, and if you ever ask them, how does that one work? Or how can I make this one better? It's not entirely apparent immediately how it works, and you're not necessarily invited to do anything about it. So we make a lot of teardowns. We make a lot of ways in which people can approach their devices and create their own. But I think that there's a lot of work to be done, and we can start chipping away at that. And when we ship a lot of these black boxes to emerging markets, to where these 6 billion people live, we see scenarios like this. Sometimes this is where we find ourselves. Sometimes literally in a place that has no roads or a system that simply is at zero, but often figuratively, where you're looking at an infrastructure that's not there. And often we have this knee-jerk reaction to create the system. But often this is what we have to deal with. And I'll take a moment to pause just to, has anybody been in a place like this? Has anybody made, in the room or online, something in the developing world? Okay, we have like 3 hands here, which is pretty good for the room. And I'm sure the folks online are gonna have other things. And I want to do an experiment that I talked to the Ara folks before. If you're online, take a picture of where you are right now and just point it at the window so that we can see where you're looking at these things from. And if we are going to look at the next 6 billion people that are going to use your cell phones, it would be interesting to get a sense of like who's going to design for them, and are you in the areas where you're designing, where your end users are going to be your customers. So we'll see what the Twitter stream gives us. But oftentimes, as I mentioned, we have this knee-jerk reaction. We want to basically go from here and to build a system. The problem with systems are great, infrastructure is great, but it takes a long time. And with mobile technology, I think you have the opportunity, in fact, you have a history of being able to leapfrog. It's almost a cliche definition now when we mention mobile technology in places like Africa, and the definition of a technology leapfrog, we always come back to how, instead of building the traditional landline systems, they built the wireless systems. And oftentimes, I'm sure that when we were trying to do that, I wasn't, but when people were in Africa and other places were trying to pull this off, I'm sure there were naysayers that would tell them, well, you have to build this other infrastructure first, or you can't. That's interesting, but there's this other thing that you have. And I think that's often the same thing in health, where traditional entrants are in charge. They have huge margins, and whenever new entrants try to come in, promoting experimentation, trying something new, promoting something that could deliver healthcare in your pocket, we're always creating these barriers to entry, hiding behind quality, hiding behind safety, with regulatory and sometimes impossible standards that are really not there necessarily to take care of the patient. They're really just to keep the same people in charge. And I think we can disrupt that. And I think that democratizing medical fabrication is one way of disrupting that. So what we do is, instead of trying to solve the system's going to be the system, we try to make the medical device Land Rovers, if you will, so that they can deal with the system as we're dealt with. Because when you put one monolithic block against another monolithic block, they fail. And they fail catastrophically. So when you build something that's so integrated that can't bend, it's just going to fracture. This is a picture that was sent to us almost a year ago now of a hospital in basically just on the outskirts of Managua in Nicaragua, where we work off a lot. And it's representative of a larger statistic that the WHO tells us, that 90% of all medical devices are donated. And 60%, so this is hand-me-down technology, okay, designed for New Jersey, delivered to Central America. 60% of those technologies fail within 6 months, and sometimes they arrive dead on arrival. They weren't designed to operate in these environments. Nobody asked people how they would use them. Nobody did follow-on maintenance, and all of them were certified great when they were manufactured at that line. And so we worry a lot about, okay, are we designing for them, and are we doing it well? Why can't we design instead with them? And our approach is to basically embrace the DIY ethos. And let me give you some examples of how that works in health. A lot of times people think, okay, you have DIY and you have health. These are two worlds that should never mix. And one of the things that we do very proactively in our lab at MIT is try to basically bring both groups together. This is a picture of a man in China who, after I think a couple of years of not being able to afford dialysis, he basically went out, sourced a local supply chain. He's in China, so he could get a lot of stuff. And he made his own dialysis machine. And he remained on dialysis with this machine that he made at home for about 6 years until the government found out. And of course, now he has a full ride because he's on the press. But the reality is, to me, the fact that you have an extreme healthcare circumstances, I feel that it leads to extreme ingenuity, and we have to harness that. Now, that's not just for places like China or Nicaragua or Honduras, where I'm from. Let's fly over to Switzerland and then go back in time to 1976. This is the apartment of Dr. Andreas Grunzig. Dr. Andreas Grunzig basically was an interventional radiologist who was very interested in how he could use peripheral catheters that were basically at the time only used for veins and that sort of thing, varicose veins and things on your limbs, into cardiac care. And he basically would come home at 11 p.m. at night and then hack, effectively, these catheters from 11 to 3, because there were engineers in Switzerland, there is money in Switzerland, he just was not in the right circles. But he DIY'd it. You can kind of see the pizza magnets on his fridge right there, and that's his neighbor making some prototypes. And within 3 years, they had what we now know in the US as balloon angioplasty. And he went on to head the department of the university that led that program in America, which was Emory. So DIY has been with us in the past, and I think it's going to continue if we harness it right and we democratize it in the right way with us in the future to make better health technologies and create outcomes. And we need that because we're spending more in health than almost anything else in our budgets, both domestically and internationally. We also can learn that in health, particularly when we're designing for the next 6 billion, a lot of these things can actually come home, and we can use a lot of these things. If you took a snapshot of Katrina, one of these is Katrina, those pictures at the bottom, and you took a snapshot of everyday Haiti in the public health system, often you can't distinguish them. In an instance, one of our own cities can become that sort of stuff, and the other way around. Health is also changing. The profiles of health are shifting. Diseases like diabetes that we had only basically relegated to rich countries like Europe and America are now actually appearing in places like India and Southeast Asia as huge population swaths go from drinking, half a Coca-Cola a day to 5 Coca-Colas a day, for instance. And then people get on jets and fly around the world. One of the benefits of globalization is that we can travel and be interconnected, but so can our bugs and viruses and bacteria. And so when we go to places like border towns in Mexico and Texas, we find that we have dengue fever. We never had dengue fever in those places, or Chagas, or schistosomiasis in Ohio. So it's diseases that have truly become global. We don't necessarily know how to even detect them in many cases. But what was somebody else's problem in the past is now really everybody's problem. So there's a big challenge, and we need to make better tools. We need to also make tools for people that are at the long tail of the medical device complex. If you're the only kid in North Boston that has progeria and needs a walker, and the only ones you can find are walkers designed for 60-year-olds, that's a long tail problem. And that's where empowering and democratizing health fabrication can thrive. And one of the ways that we make it thrive is we use kits. We started to play with kits a few years ago, and one of the things that we found is that kits basically are a gateway to rapid prototyping of specific sectors. They're a curated set of parts that we've all played with. You have kits for electronics. You guys have really interesting kits for electronics, but we have playful kits for electronics. We have bicycle kits. We have food kits. We have weather station kits. The first steam engine was actually shipped as a kit. The first Apple computer was shipped as a kit. So one of our interests was, what else could we apply as a kit mentality onto healthcare? So we make big kits sometimes. We make kits like the Solar Clave, designed by Anna Young and her team at MIT. And this is basically, it looks like a Tinker Toy set that actually converges onto making a surgical sterilizer that you can put together, put it in the field, you point it at the sun, and you have clean surgical instruments in about 25 minutes. And we work with people and we give them the tools so that they can tell us, I didn't like this part of the kit, can we modify it, or I built it this way. So it's not just assembly from 0 to 10. It's assembly in a nonlinear fashion, and that's critical. And then we find people like Daniela Urbina in Estelí, Nicaragua, which is the center part of Nicaragua. She basically, without any kits, without even before we arrived, she found, she had a stethoscope and it broke. And I don't know if you've played with a stethoscope. It generally has this little plastic part. And so she went around the hospital and experimented with different pieces of plastic, cut it up in little circles until she found the one that worked. And if you notice, it still had the Sharpie, the little red Sharpie markers. She settled on overhead transparency slides. And she was embarrassed by her solution because it was kind of a hack. She didn't know the whole hacking history at MIT and how we would have otherwise given her a huge conference auditorium to talk about how she made it. But for us, this is a lost opportunity, but an opportunity that we harness to say, how can we find more Danielas out there, both in the American healthcare system and in Nicaragua and in Central America and other places, and empower them beyond what we can potentially scale on our own by traveling to a bunch of different places. So we made the MediKit project, which stands as Medical Education Design and Invention Kits. And the idea is, could we create a repeatable set of parts that are standardized, that democratizes the design process, basically Legos for medical devices. And we drew our own map, not as full as the one that was shown earlier, but basically we started to deploy a lot of these technologies and approaches around the world in areas of the world where we know they're not necessarily going to be as connected as we're usually connected. And then people respond in kind and said, this is what we made. And this is what we're going to make with you, which is a lot more exciting than when they just tell us what they want and then we make it for them. You can build things like an asthma nebulizer. So this is a traditional asthma nebulizer. It costs about $80. And essentially, it sprays medicine. When you use one of our kits, you can mix and match some parts, and then you can converge and make up a very simple device, but it's a life-saving device, pedal-powered $10 nebulizer. And when we look at the actual curves to see how well it performed against the commercial one, it tracks basically the performance of it without any electricity, and more importantly, with a transparent design that people can replicate. And then it's no longer that black box design, because most of the time when we walk into places like Nicaragua, they point at this device and they point at the blue thing and they say, that broke. And what they don't understand is the magic really happens in that little green thing on the bottom, which is the aerosolizer. And once we start to demystify that process, then they come back and they say, well, we have this broken, how can we make this, instead of, can you fix it or can you make a better one? And that's where it gets really exciting. And I think that's what we have to keep in mind when we're designing for the next 6 billion. Because when they go from this and they start teaching other people, they get confident. And the hierarchical structures start to get flattened. So this is a nurse teaching a doctor. That's actually very rare in some of these countries. And then they get very confident, and then they start to hack them, and then they produce pediatric nebulizers in this case, and so that they can basically treat 2 people at the same time, and they use toys and they use other accessories to really make it their own. This has become so successful today. We now have a project in America called the Maker Nurse Project, supported by the Robert Wood Johnson Foundation, where they said, could we do the same thing of democratized fabrication and find inventive nurses, maker nurses basically, in America, and figure out what tools do they need. And eventually they're going to use our medic blocks and kits, and maybe they could potentially, in the next few years, use Ara blocks. One of the things that we do when we're creating these systems is we have to focus on creating a language of design. And what we mean by that is, how do we, instead of trying to create a very large protocol of use and instructions, how do we make it so that you can just look at something and you recognize it as easily as many of you know the 2x3 Lego block. You've internalized that. You've stepped on them, you've found them, you've played with them, but you've internalized that shape very, very well. How do we do that for other shapes that are not going to be that standardized, that we will often find in medical technology? So we do that for diagnostics. We play with shapes, we play with colors. We evolve the different designs. These are some diagnostic kits where you can make clinical chemistry tests. We provide companion printers so that they can actually use their own antibodies that they can grow in country that sometimes we might not have access to. We also make a lot of tangible prototyping tools. One of the things that I can't stress enough is that even though we may come up with the best digital simulations and approaches of how to build something, if you're, as Daniel pointed before, is if you're making something in country, or if you're trying to engage your consumers as designers, digital may not always win. They may be more comfortable with their hands. So in this case, we did blocks, for instance, because we wanted them to design microfluidics. And we had this whole system based on CAD where they can actually go and use a process called xerography, which is basically cutting using a very fine CNC cutter to make lab-on-a-chip devices. But we also realized that not everybody's going to be, you can be a really good laboratory technician, but not necessarily be a good CADer. So how do we get them to use their hands in the way they're comfortable? So we made molds so that they can basically do different blocks and shapes. And then we can embrace local supply chains. We use a lot of toys because toys are almost everywhere. These are some microscopes that we've deployed to test STDs. And then when we look, if you have to peek at our whiteboard of what's next, these are some of the things that we consider when we make our own blocks. And I think these are some of the things that you're probably already considering. The sensor layer is getting more advanced. You know, we're going from electronic sensors to gas sensors to electrochemical to molecular diagnostics that are portable and miniaturized to optical sensors. There's a whole spectrum of things that we can now detect that we couldn't detect before that are now almost commodity prices. We have to consider active or passive situations. Not everything's going to be passive necessarily. The reality is if you have a user in emerging markets that's actually interested in what they're doing, when you've provided them a module that gives them a sense of sophistication, active can actually be very, very, very useful. But it's a decision that we're going to have to take either way. What is the engagement layer? It's going to be very different to design for a culture in Latin America or in Southeast Asia than when you design for our rapid multitasking American culture for Texas and New Jersey. So think about that. Don't discount it if you're going to when you're making your UIs and your interaction layers. And then there's we call it the so what layer. So you've graphed all this stuff, you've told me everything, and you've logged it. What are the insights? What are the actionable insights that I can glean from this? And what are going to be their insights? Because if you think that there's an opportunity cost for your time and money, they're going to have a bigger opportunity cost to deal with in many cases. So make sure that we deal with the so what effect in health. We know a lot about how to personalize things that go in our pocket, and I think we've saw previous presentations that talked about that. And this is one area where it's going to be really interesting when health is concerned. How do we personalize it? Because when one person says personalization, the other person on the other side of the FDA might say standardization and repeatability and certification and evaluation. And we have to balance each carefully. And our own approach is really tilting it more towards what do people want at the end, and how do we thrive on that long tail edge that I described earlier. We care about interoperability, both physically and intangibly. This is the free universal construction kit made from a design group in Carnegie Mellon in Germany. And if you notice, basically they've created interoperable blocks amongst the different construction set families. And I love this picture. We've actually printed these and played with them, but I love what it says. It says, you know, not only am I creating something, I'm creating something that can talk amongst families, thereby hacking that system. Some of our newer construction kits look at how do we address adherence. We have adherence technologies, but one of the things that we thought about is, you know, it's a 300 billion problem. There's just not a single silver bullet approach that you're going to have to take. So how do we create construction kits so people can make their own smart medicine bottles? And make them for less than $20, not $60 a pop, because the people that have issues have like 6 different medications that they have to take. So investing $700 into a smart pill bottle collection simply is the type of thing that leads to digital divides in our healthcare system, and certainly in the next billions people's healthcare system. we've created modular diagnostic systems. These are some of the newer modules where you can look at a lot of different both diseases and electrochemical signals in different ways. We can look at pregnancy and STD combinations or swap them out and test Ebola. We can look at clinical chemistry using paper microfluidic blocks that you basically just mix and match, just like a Lego set, if you will. We can create vertical flow-through tests that use buffers. We can look at optical readers and put them on top of our clinical chemistry results so that we can digitize some of that information. And when we look at Ara modules, I think one of the interesting things is that then you can add computation to these reactions, which is something that usually required a lot of instrumentation. And if that computation and diagnostics are combined, then you can do a lot of assays that would ordinarily be very hard. Microscopes are some of the earliest technologies that have been developed for phones, and we want to democratize that. So this is one of the kits where you can make different microscopes using different filters and basically make your own and attach it to an electronic device. If you want to get quantitative, you can do spectrophotometric measurements, which are basically the workhorses of laboratories around the world in developing countries. Some of the immediate applications of a lot of these things and some of the things that we've worked on that are less construction set, but more tangible applications that you can apply in healthcare in emerging markets are things like maternal health. A few months ago, we created something called Smart Birth, and the idea was how do we look at this convergence of interest between people that want to do checklists, people that want to have real-time information, people that want to expand on training, and people that are deploying individual birth kits for midwives in rural areas, for instance. And individually, these verticals are almost never compatible. The people that want to do checklists want everything done in an institution so that they can track quality, but the people that want to do birth kits want to empower those rural regions so that babies can be born anywhere instead of having to die on the way to the hospital, for instance. So one of the things that we started to assemble was something called Smart Birth. And the idea was, could we take one of these kits and sensorize it and then add just-in-time training capabilities so that your phone acts both like a flight data recorder for exactly what's happening as you're using the different instruments, but could you add anything from augmented reality to just image recognition so that you can look at if somebody scans a umbilical cord clamp, it'll tell you just in time how to use it. It'll tell you what you need to use next, and it'll tell you what type of things you need to follow on, and then we can record the whole event. And then you can capture things that have never really been captured before, which is what really is driving the birth of all these babies and the survival rates of all these babies in places where we would just write it down as baby born in the middle of nowhere, no information. And then we can actually start feeding back some of these loops into the app so that we can do smarter algorithms for care. We're looking at diagnostics and how we can go beyond your standard diagnostic. Who's here taken, and same for the online crew, who's played with a pregnancy test before? So we have, yes, sir. Good job. One of the things that we do a lot is we take apart pregnancy tests and other types of rapid diagnostics. And one of the things that we've expanded is how do we take the pregnancy test from a yes/no result, which is generally what we have today, to one where we can actually use it as an interactive display, if you will, driven by the chemistry. So we use this for tuberculosis. TB is a disease that still has about 10 million cases, almost 9.8 million cases a year, and still kills quite a few bit of people. And it's completely curable. We have antibiotics that work, but if you don't take your medication, and a lot of people fail to, it basically leads to a death sentence where you develop multiple drug-resistant TB, and your cost of treatment shoots from around 100 to around 150, depending on where in the world you are, to about 1,000 plus, maybe 2,000, and 2 years. So it's 8 months for normal treatment and 2 years for extreme treatment. So keeping people on their meds was really important. And one of the ways that you do it is you send somebody to people's home to test, not to test, to just look at them swallow the pill. And And most of these people apparently were not showing up to work. So what we did is we made a new type of diagnostic called interactive diagnostics, where MIT actually secured a lot of IP on this. And we turned it into a way where we could actually create a secret code that can only be developed if the metabolites of your system basically unlock the code. And those metabolites can only be generated if you've taken your medication. So we're not adding RFIDs, we're not adding scanners, we're simply doing it with chemistry, which is compatible with mass manufacturing schemes of generic and proprietary pills around the world. But then the next thing that we do is we give people rewards. It's not just a big brother effect. We need to somehow hack the behavior so that if you are giving us the right code, if you take your pill, it generates 5721. We get a code back and we give you a reward. And when we first thought about it, we thought, I don't know if you remember, maybe 4 years ago, if you Googled anything with business and international development, you would get microfinance in some of the top hits. And we thought, great, they're going to get a microfinance credit, it's going to be great. And when we went to our partners in Nicaragua, they said, that's just going to be, it's going to be a nightmare. You're going to have money laundering issues, you're going to have transaction issues. Why don't you just give people cell phone minutes? And the important thing here is we did, and that's when really the program and the interest in the approach really started to take off, because it was genius in that regard. It was virtual currency that we didn't have to invent, that everybody was already trading and everybody wanted it. It was a very liquid reward system. But had we gone in with a black box approach, and had we not been open to their ideas and welcoming and saying, how do we treat this as a kit, as a construction set where lots of solutions could potentially be piloted, we would have never gotten to where we are with Adherio. We extended the platform now that we can tell what people are telling us remotely. Now we can actually make detection mechanisms and verify them at a distance. And we said, how else can we apply them in health? And what else can we do? And we started to look at real-time systems. We have real-time systems for traffic. We have real-time systems for weather. This is a really neat project called WindMap that shows you real-time weather systems. But we don't really have a real-time system for health, not really. And when we look at what happens this is a picture taken from the New York Times a couple of years ago, that tells us, for instance, the path that the cholera outbreak in that country took. But we know all this almost 2 years after the fact. After all those people died, we collect all the data records and we rebuild them into a scenario that basically didn't help anybody at that time, with the purposes that maybe it'll help people in the future. So how do we build a real-time system? And one of the things that's often missing in these systems we have fantastic information systems. We have fantastic data scientists often behind them. But to have predictive value, we think you have to have what we call, what weather people call ground truth diagnostics. How do you know what's happening on the ground beyond what somebody sends you over a text message? And one of the things that we're doing is working with the Gerke Lab at MIT and other collaborators in basically deploying the Foursquare for disease, where people can just either submit something that actually comes out of a portable diagnostic found in their first aid kit that can look at lots of different pathogenic diseases, so that we can have an early warning system in real time, not just after the fact. And hopefully we can save some lives with that and respond. We've already done this for environmental sensors. We've deployed it with very basic water sensors. And the idea, if you notice, somebody's actually putting one together on the spot. And the reason we did that is that if we just had given them the device in a final, in a final constructed set, we would be basically doing another citizen science project. But what we are more interested in is, yes, we're interested in what's happening with the environment and water and quality in places like Christchurch and Berlin, but we're also interested in what are people interested in checking for in the first place? What insights can we glean about what they're going to make? And what happens when they rip off part of the card and they replace it with their own and they achieve what we call design for hack, which for us is the truest level of success in a technology transfer project, because they're no longer obedient to what you originally designed something. They've gone beyond that approach, which is something that Ernesto Rosa calls technological disobedience. So we design all our devices with that transparency, that construction set approach, that design for hack to invite people, not just to hint at changing it, but to really encourage it, so that we can do more of this, in this case, environmental testing. And we've deployed it in different places. So what are some challenges that we are tackling next? But we can't be the only game in town. And I hope that you take some notes and see what other modules that you could develop or ecosystems. Nutrition is going to be a big one. The reality is, if you think cell phone companies and consumer electronic companies have found emerging markets, you should see the marketing machines that fast food companies have, and junk food companies. So the reality is, when I was growing up in Honduras, for instance, going to a burger joint, to an American fast food restaurant, was a status symbol. You would put it on your cup holder because everybody could, so we could show off, which is terrible when I look back at it. But that's how we grew up, and the result is that you have these extreme situations of malnutrition. And malnutrition can be underweight. It's not just skinny kids anymore, but you can also be overweight and be malnourished. 20% of the kids in El Salvador are overweight. 30% of them have stunted growth. 380 million people around the world have diabetes. 24 million in South America, 55 million in Africa, 72 million in Southeast Asia, 138 million in Western Pacific. And unlike the ones that you would find in America and Europe, all of these numbers have a huge hockey stick attached to it. It's only getting worse because we haven't really tackled the problem. Only 46% of them have access to the diagnostics basic glucose sensor. I mean, one of the things that I think would be amazing to come out of an Ara module, beyond the stuff that we make in the lab, is let's make a better glucose sensor. You're already given, you can get rid of this razor blade model. Because unlike a glucometer where you have to amortize the cost of that device over many different diagnostics tests, you're getting one. And the BOM for these things is extremely low nowadays. But again, we're flooded with this black box mentality, especially in diagnostics, and that's why people in Nicaragua simply can't afford the $2 to $3 a piece diagnostics for glucometers. You know, the protocol for and the standard of care in places like Central America for diabetes is basically if a mom has a child with pediatric diabetes, and they can't afford a glucometer, what they tell them is every morning before breakfast, take a teaspoon of urine and taste it. And if it's sweet, you have to do something about it. We can really do better than that. And that's something that's going to be much better, I think, much more interesting as an engineering challenge, as a design challenge, as a business opportunity than making another accelerometer for them and then displaying an interesting graph. I think it has to be about interventional. It has to be about creating change. Maternal health is another one. 280,000 moms a year die because they didn't have access to the right care in pregnancy. And along with them, 3 million kids a year. 75% of these die giving birth. We can give them better access to diagnostics, better ultrasounds, better respiratory care, better training, as I mentioned in things like smart birth, but there's many more things that we can do beyond just hoping that system matures to try to catch up with them. We need medicine, but we also need information and remote access. Things like sensors that you can look at a distance and see when that contraction is coming. When they may or may not have access to the right care, so that we can do something about it better and save some of those kids instead of just counting them and doing more statistics. And I want to be clear. I think that one of the things that is different with hardware, and I know a lot of us work in software, is that the opportunity that we have in hardware is diagnostic and it's interventional. It's not just gathering information for the purposes of data spectatorship. We often do that in public health, and then we just count all these things and we make interesting charts. We have to start doing something else so that we can bend some of those charts and change their direction. And not everything is going to be something that fits in your pocket. You know, when we think of global health and emerging markets, we have this notion that we have to make like the REI camping stove for point-of-care diagnostics or something. It's got to be something that's portable. It's got to go out there, and we're going to use it with a solar power or wind-up machine, because the reality is that's one picture, but that's not the only picture. There's a huge opportunity in small to mid-scale institutional laboratories. You know, when we travel around the world, and when I was growing up, one of the things that always struck me is you would find in some towns, and I'm really not exaggerating, as many laboratories as you would find coffee shops in places like Boston. You would turn the corner, there's another laboratory. And they're not advanced biomolecular laboratories like the ones we would find at the Broad across the street from MIT or anything like that. These look like mom and pop institutions that have a microscope and a spectrophotometer and maybe, if they're lucky, an ELISA plate reader, and then basically whatever's in between their ears to make an analysis. And they need tools that are not just rapid diagnostics that are consumables that can add up. They need analytical tools, and affordable ones and reliable ones, and ones where they can harness computation, just like things like what platforms like what you're going to build can provide them. A country like Nicaragua has about 2,100 health establishments. Half of them are private, and they all have laboratories. And these are those mom and pop shop lab bodegas that I'm talking about. We have to look at workforces as well. Beyond, you know, you have to look at, there's pharmacists, there's doctors, there's nurses, and they're all growing, and they have an increasingly big role in how healthcare is delivered. A pharmacist in a developing world and in emerging markets has a lot more power than a pharmacist that you would find here. They can actually issue prescriptions on the spot and treat you. We need to think about tools for them. There's 32 million nurses worldwide, and they're growing, and they provide 80% of clinical care around the world. We need to give them reasons for them to stay in their countries and in their hometowns instead of trying to migrate to the cities or be exported to industrialized countries where they find the instruments they need and the salaries they have. But we also have community healthcare workers. 25% of kids under 5 could be saved by scaling and equipping community healthcare workers around the world. That means basically the equivalent of hundreds of thousands of small surgical strikes against diseases like diarrhea, pneumonia, malaria, malnutrition. Simply, sometimes it's just a visit that people can make, but sometimes they can be armed with a stethoscope or diagnostics or something that can basically augment that experience and that touch point of healthcare when they might be the only people around to provide it. And it's a growing group. Sub-Saharan Africa has 250,000 of these. Brazil, 240. America has 175,000 community healthcare workers. Just look at New York City's HealthWorks initiative. And of course, there's places like India that have like 2.5 million. And are going to continue to grow. And if you're interested in that, look at programs like the 1 Million Community Healthcare Worker campaign by Prabhat Singh at Columbia University. They all need better tools. Nobody is designing tools for these groups. And I think this is a huge opportunity. One that comes with reimbursements, one that comes with people that are interested, that are going to work with you, but that you have to go and to these places and do it the right way. And, you know, we talk about diabetes, we talk about the reality is non-communicable diseases are advancing, but we can't forget about infectious diseases. The reality is we've made a lot of headway with vaccines and eliminating diseases like smallpox and maybe hopefully things like polio one day. But there still remains the big three, things like HIV, malaria, tuberculosis. Diseases like dengue. 1/3 of the world's population is at risk for a disease like dengue, which causes potentially hemorrhagic fever. And we have 50 million new infections annually, and there's no vaccine for dengue. And even if there was, the world's largest manufacturer, which one of the, like Sanofi, doesn't have the capacity to fill even a fraction of those new infections. So we have to prevent it. And prevention means real-time epidemiology, which is why we're working on trying to disseminate these types of early warning systems so that we can mitigate the disease before it gets out of control. NCDs, non-communicable diseases, remain one of the fastest growing areas. This is the double-edged sword of development. As people get wealthier in these areas and we go from eating a modestly vegetarian or grain-based diet and start eating fast food and all these other wonderful things that processed food innovation gives us, we start getting things like what I mentioned, like diabetes. But we have other things where we can save these kids from diseases like polio and smallpox, just like the rest of us. Now they're at a higher risk because just the natural progression of life and disease exposure to things like cancer. In 2020, 70% of all cancer deaths will be in the developing world. Just think about it. That's 5 years away from when you're planning to launch the Ara phone. Most of that problem will be within these next 6 billion users. And there's some immediate things that we can do about it. We have pap smears that get delayed because they're not digitized, so people wait for months on end waiting for the results as our disease could potentially progress. We have mouth and skin cancers that just go unnoticed until it's too late and they start to spread. We have chemo that's hard to administer because we don't have the right digital machines to do it. So think of all these things and think, not as sometimes it'll be a phone that can save the day, but sometimes it'll be something else that a phone can augment, or modules that can provide some of the computation to solve some of these problems. And lastly, one of the things that is rarely talked about because it's so overwhelming from all these other areas is mental health. We're starting to have lots of these conversations in the States, but when you look at these next 6 billion people, you find that in a place like China, with 1.2 billion people, it only has 15,000 psychiatrists. India has 1/5 of that ratio. 1 billion people, 3,000 psychiatrists to take care of their mental health population. And China and India are easy numbers to make. I mean, you can almost take any type of industry, I get that, and generate huge numbers from these two countries. So look at other places. Indonesia has 450 mental health care workers for 210 million people spread over 13,000 islands. Now, if that's the case for telemedicine, if that's not one for telemedicine, I don't know what a better one is. Where basically you're not even necessarily exchanging medicine in some cases. Sometimes it's your traditional therapy that you can do with communications and sensors. 1 in 5 South Africans suffer from mental illness that is severe enough to debilitate their daily lives. And in Latin America, one of the continents that is basically scourged with immigration, exiles, and high murder rates, countries that basically use less than 2% of their budget to attack this problem. So again, this is another opportunity for leapfrogging and disruption where we just simply can't wait for these systems to mature. And it'll be a long, hard just fight. One of the things that I really like what Neil Stephenson has said before is like innovation can't happen without accepting that the risk that it might fail. And it's happening in really dangerous places before, and it's going to continue to happen because the world's not getting any safer. But that doesn't mean that we can't continue to try. And what I would encourage you to do is, as you try to generate the next generation of modules and systems and sensors and devices to empower people in health, go back and make your own map. And see how you can allow them to play and really play, and see how they'll respond. We've created our own hardware expeditions. I'm pretty sure that you can make your own. And remember that health is everywhere, that you need transparent designs, that you need to embrace a design for hack mentality and let them open up the black box to really co-create. And think of how these modules will eventually become part of an ecosystem that play together, not as yet another universe of smaller black boxes, but truly as a construction set that can have an effect on health. And we would love to help you. Thanks.
All right. Thank you, Jose, for a great talk. All right. And now for our next session. So I think I may lack the introduction charisma of my colleague Dan, but I will be happy to introduce Scott Turner, senior researcher, and Scott Summit, the director of Bespoke Products, both from 3D Systems. They're going to talk a bit about the power of 3D printing and the capabilities that are going to be brought to the Ara platform from that. And it looks like we have some fun demos in store for us as well. So with that, I'll hand it over to these guys to take it away.
Thanks. Hi, so yeah, we focus on 3D printing, and I want to convey to you just why that's relevant in the upcoming century, and especially with the products that we're talking about designing right now. When you look around you, everything that's in your world is the result of mass production. We're surrounded by mass-produced, identical stuff. And that, if anything, is the definition of the 20th century. This is when we successfully navigated the waters from okay, can we do the other slide deck, please? So when we successfully navigated the waters from handmade artifacts, handmade handicraft, to mass-produced identical stuff. Could we do the other deck?
All right, just bear with us 1 second here. We're going to switch over presentations for you.
Great, thanks.
Wrap it up in a minute.
There we go. So yeah, we successfully navigated the waters from handmade artifacts to mass-produced identical stuff. And with that, identical is really the operative phrase, because that's how we measure the success of manufacturing. It's how identical those parts are, how devoid they are from individuality, of uniqueness, of anything that has individual style or personality. We're really shooting for getting the most identical stuff possible. And so what we really arrived at was the age now that we're in, which is the age where we're very successful at making clones. We're successful at making identical products from one to the next. And overall, despite the cynicism, that's really a good thing, because we can create products that are well-tested, well-designed, well-engineered, but most important, of course, really, really cheap. Because now, of course, we're in the age of form follows finance. And what we traded for that is very low part cost for very high upfront cost. So, okay, that changes everything, because when you get your parts, the trade that we made in that is that designers now are really discouraged from taking risk. Because when you have a high upfront cost, if nobody buys your product, all of your sunk costs are sunk. And so designers are really encouraged to create vanilla, to create really good tasting vanilla, but still it's all about vanilla. That if you're creating that salted caramel stuff, you might sink the ship. So you really want to stay in that middle road and create the safe stuff. And your high upfront costs come from travel to faraway places to get your manufacturing done very, very inexpensively, and all the tooling and debugging that's needed to get those parts made so that, again, you can get high upfront cost, very low part cost. And designers and consumers entered into a pact, and we all kind of buy into that, or at least we traditionally have, because there has not been an alternative that's really terribly viable. So that's what led to the clones of the 20th century. But what we have now is we're transitioning into an age of from mass-produced identical stuff into have it your way. And one of the tools, the expectations from the consumer are changing, and the capabilities of the designer likewise are changing. One of the operative tools there is, of course, 3D printing. Now, what 3D printing can do is it allows you to go directly from computer file into physical artifact without any of those other two phases, the travel to faraway places and the expensive upfront tooling costs. You go directly from design to part. So you can make a unique artifact every time, and you can create a part. The cost of one part is no different from the cost of many parts. It's all by way of going through a 3D printer. So keeping on the same light metaphor, let's say you are a student right out of art school, and you want to create a lighting company and housewares company. Well, traditionally, that's prohibitively expensive, of course, so you don't even go there. But now you can actually do it, and here's a case of that. Guy sleeping on his friend's couch, right out of art school, saddled with student debt, creates lamps. And the difference is these lamps are 3D printed. So he has no upfront cost, no cost of risk, no inventory. So, and he can also turn on a dime. Every time he has a new idea, he can model it, put it out there into the market. So all of a sudden, he's got a whole lot of products in his product suite, as many as some of these old established companies. Now, the difference, though, is that he has no risk. So if nobody buys any of these lamps, he's lost a bunch of ones and zeros. Very easy to part with, no cost. And because of the flexibility of geometry that he has with 3D printing, he can make complex shapes that nobody's ever seen before. He can really start creating these very elaborate, exciting, engaging forms that draw you to it, that have meaning, and that get people excited. And all of a sudden, within a few years, he is one of the more influential designers in Europe. But he did it all with no upfront cost and no cost of risk. Now take that a step further, and you have Nervous System here out of MIT. A couple right out of school, they create a jewelry company. Now the difference here is, again, 3D printed stuff, but you can go into that, the processing chunk in the corner there. You can start modifying the details, the gravity, the attractors, things like that, and you're changing your jewelry that will be created for you. It's then 3D printed and sent to you. And it has more meaning in a sense because it connects directly to you. It's from you because you co-designed it. And you know that nobody will ever have one at all like it. It's unique to you. And that takes advantage of one of the other attributes of 3D printing in that you have nearly infinite control of the geometry that you can create. You can create forms that are prohibitively complex by traditional standards. Here's an example of a bag that we did for Will.i.am. It's all chainmail, but it was all printed in its chainmail assembled state. The thousands of links that are created it came out of the machine exactly like it is. It's nickel plated, so it's just the side of bulletproof. But here's the other tweak, is that every link of that chain is unique. No two are identical because they're driven by algorithm. So there's a swirl pattern that runs through the whole thing to make it that much more interesting and intriguing. In fact, not only is complexity free, complexity is actually cheaper in a lot of cases. When you look at the solid block here, that's the traditional way to make something. You'd have a block, you drill some holes in it, call it done. When you're 3D printing something, on the other hand, you're not paying by the process, you're paying by the molecule. So the more material you don't have to print, that translates directly into cost savings. So in this case, this highly optimized lightweight product costs less than the traditional solid product. So you can put all these together and look at a couple of the variations that can come from this. For example, let's say instead of getting a guitar the traditional way, you go to the guitar store, try some things that are kind of the sound you want. Let's say you designed the sound. You design the tone, the timbre, the warmth, the sustain, the bass, the treble. You design the attributes of the sound that you're trying to achieve. The algorithm creates the guitar, and then you simply print it, and that guitar is sent to you, and you have a guitar that was designed by you based on the attributes that you're searching for. This is the new way of looking at consumer-driven product, where the consumer is a co-developer of your product. In fact, in this case, the neck plate there, 3D printed stainless steel. Even the picks are 3D printed nylon based on the individual preferences of the user. Here is the exoskeletal robot created by Exobionics. We took this mentality to them and looked at creating modifications to the robot that would connect it better to the person, because that really has everything to do with the usability of the product. So in this case, we 3D scanned one of their test pilots, and we took portions of her body from that scan and let those drive the forms of this new design. This was done by Gustavo Frick, sitting here. Those designs could not only connect her body more accurately and more confluent to the product, but also it's more ventilated, more flexible, and there's a degree of artistry that can be put into it, again, because we have complete control over the geometry. We can make it as beautiful, as sensual, as fluid as we like. And then we took a walk around Budapest with it. We took the same idea to scoliosis. This is right now state-of-the-art, best money can buy in scoliosis treatment. And people wonder why girls don't wear this for 2 to 4 years, 22 hours a day, as they're supposed to. Well, we took the same approach. We 3D scanned the girls, correct their spine digitally, 3D print a brace that is not only more ventilated, it's lighter weight, it's more discreet because it hides under a t-shirt, but most importantly, when they look at themselves in it, they're okay wearing it. They don't feel like a science experiment, so they're that much more willing to wear it for the full 22 hours a day, 2 to 4 year treatment. So all of a sudden, good design and the flexibility offered by 3D printing translates directly into the quality of the medicine. Take the same approach towards casts, fracture stabilization. Here's old school. This is what happens when you can 3D scan a broken arm, in this case of an 8-year-old girl, and 3D print a brace. Or in this case, 2 girls with broken tibias, 3D scanned and 3D printed. 2 things that happened that were a little bit surprising. One is that they healed in record time. That was fortunate. 2 was that the girls did not want to give their cast back. So now anybody who's ever had a broken arm or leg, that's not really the process. Normally, by the time you're done with treatment, you wouldn't touch that cast with fire tongs, but they fought to keep them. So in retrospect, it's probably irresponsible to perform unlicensed medical experiments on your angel round investors' kids, but it worked. So all's good. Same mentality here applied towards prosthetic limbs. If you lose your leg, is this really the best thing that you can have? Is this really something that supplements your body, that complements who you are, your personality, your form, your shape? Well, if you're her, you don't really think so. In this case, we 3D scanned her other leg, mirrored it, designed the prosthetic limb, the surrounding, that recreates her form, but also captures her personality and her style. We can do the same thing here with number of materials. Herringbone for a person who preferred herringbone, or this guy to match his tattoos. We have all kinds of opportunity based on the vast flexibility of 3D printing and the way to connect a mentality, a design mentality that connects design intent, user needs, and the way to manufacture. So we can create a product now that's far more meaningful to the user, that actually captures something about their personality, something about their real design intent, so that it's not simply a one-size-fits-all mentality. We can actually capture the individuality and the personality as well. Thanks.
Scott. As usual, following Scott is difficult. His slides are beautiful and his stories are great. So I'd like to take a quick second. My name's Scott Turner, and I'd like to just quickly calibrate, do a survey of you in the room so I can calibrate my talk. So who here envisions themselves doing custom shells, being involved in the process of creating custom shells? Okay, few. Who here has 3D printed a part themselves, sent the data to a printer, peeled it off, dealt with the After Effects? Okay, for 1 year? For 5 years? For 10 years? For 20 years? For 26 years? All right. 92. All right, that's pretty good. It's rare to have another dinosaur in the room. So I've been doing this for 26 years. And Project Ara and the fulfillment process is an amazing opportunity. It's one I'm excited about. I get up every day, and my first module is going to be my last slide that you'll see here, and I'll try to explain when you see it. So what I'd like to start by talking about is mass customized manufacturing. So with Project Ara, obviously, we need to produce tens of thousands, hundreds of thousands, millions of unique objects. And is that being done today? Or is Ara going to be the first project to do that? Well, it's not the first time we've done this, okay? There were two graduate students in Stanford in the mid-90s, and they had an idea to replace braces. Has anyone here had the opportunity to use the aligners from Align Technologies? Okay. So what their idea was to take a digital model of your teeth with where they were and then create the computer model for where your teeth should be. And then they iterated a number of steps in between that migrate the teeth from where they are to where they should be. And on average, it takes about 25 aligners and approximately a year for a patient to have their teeth moved by wearing these clear plastic retainers on their teeth. And so far to date, Align Technologies has treated over 38 million cases in 45 countries. So from that time to now, that's a quantity of 1.5 million patients. Over 38 million aligners have been produced. And it was our technology, our stereolithography technology, that created the intermediate steps because they just don't exist. And that's what the aligners are based on. And that process operates in a lights-out factory that's fully automated and has the capacity to produce 80,000 unique aligners in a day. Now, I don't believe they produce 80,000 every day, but based on demand, they can produce 80,000 unique aligners in this factory. And it's all based on digital manufacturing using a stereolithography process. So we manufacture today using our technologies and 3D printing. So now let's talk about Ara. And let's talk about a couple of the images here that were part of the research. And I take these very seriously because those of you that made them, that are part of the community, that shared them, had to take the time to do this by hand. You had to go to the craft store, you had to get materials, you had to really care enough to do this. And you can see here, I mean, 3 very distinctly different looks of what they'd like their Ara device to look like. And for me, this is one of the inspirations of what we need to do for this community. And so let's talk about some basics on how we do that and how are we going to implement this process of creating these unique shells. So first off, let's talk about what we are and what we aren't going to be fabricating. Oops, sorry. So the bases, the circuit boards, the sheet metal shields, those are going to be made by you, the module manufacturers, using conventional manufacturing processes. Then there's the shells, and there's a standard shell shown here. Now, to get that shell to look like the inspiration that the community shared with us, there's 3 things that we need to do. And I'm not aware of a printer that does them simultaneously. But these are the 3 pillars. So we've got texture, we've got to have 3D textured objects, we've got to have full color, and we want to have multi-materials. So here's a digital version of people's inspiration in the configurator that we're working on in the program. And by simply adding that 3-dimensional element, we can create a visual language that describes the function of those modules. Tells you what they are without having to have words or ugly other text on them. So here's the first digital version. So now here's some basics about 3D printing. And this is going to get pretty rudimentary. But so what we can do, and the language for 3D printing shells our individual bodies. But we're going to use a different word for that. We're going to use the word meshes. Okay? So we have the standard shell, which in this slide is a mesh that's watertight. We have a picture of the cat that everybody likes, and we've converted that into a three-dimensional mesh. We've overlaid those two meshes together because we want them out of two different materials. Okay? And so what we're going to do then is we're going to print those by specifying different materials for each of those shells. So if you do this simple process, voila, you have a custom shell, Ara shell, with a cat. So what does the data look like? What are the things we've got to work with today? Well, the STL file, who's heard of an STL file before? Those printers, especially you in the back. You've been doing this for a long time. Okay, so an STL file is used for almost every single part that's printed worldwide today. This file format went from an idea that Chuck Hull had when he invented the stereolithography to the standard for 3D printing. And it's very simple, which is why it's been so successful. It's triangles. It's a mesh with a unit normal, and it can only be one mesh by definition. Okay? So let's look at what we're trying to print. So we said multi-material, and in order to do that, to specify different materials in different places, we have to have multiple meshes. So we're already kind of off the road. But it works today. You know, we do multiple material printing. Some of our competitors do. So the software can figure that out. Now let's add the next component that we have to do. We want to do color. Okay? Color is one of our pillars for making this vision come to life. I don't know where color applies to triangular meshes. And now let's do texture mapping. So we want a texture map. We don't want to have to model every little wrinkle or a herringbone pattern. We want to use texture mapping technology. Okay? So let's come back to our friend the STL file. So here it's 3 vertices, a unit normal, one single body. So are we going to launch you off and just hope for the best? No. So a big part of what 3D Systems is going to bring to the project is the data flow and supplying tools for you, those that are going to be part of the shell customization process, to use to feed this new fulfillment process that we're building. Because it's a very unique printer, fabricator. So some of these tools, I've got a conceptual slide here today that talks about some libraries that we can include. And one of the things we're going to do early on in the program is we're going to incorporate the OBJ file. And for those of you who don't know what an OBJ file is, it's used for rendering, for gaming, for those applications where you want things like 3D shapes, colors, texture mapping. And we're going to use that as an entry point for getting data into the system for customized shells. So let's look at a couple of examples real quickly. You know, things we're going to want to do, things that we've done in the past that people like. Taking images, you know, decimating them into large pixels, and then elevating those pixels to create shadows and color. Okay, uniqueness. This is another example. Taking sound waves, music, MP3 files, converting those from the visualization that people do with music into physical objects that represent that music and artistic in nature. Another example is color. Taking a very crisp image, decimating it down, and making it more interpretive, less direct. And with Ara, we have this opportunity of having a lot of sensors, all kinds of different sensors. And here's just one imaginative way to leverage that is by taking your breath and turning that into geometry based on how you sense it and amplify it. So these are tools. This is a data path, a flow that we're going to create and provide to the development community in a conference later on this year. So lastly, once you developers do your magic, use our library, do your own creative things with data to create unique shapes and images, we're going to help you by validating those. So the first thing we're going to do is make sure the meshes are of good integrity so that when they get sent back and ordered, they get delivered. They print properly. The next thing we're going to do is we're going to make sure it fits in the endo. Because if it won't fit in your endo, it's not going to be a module you can use. And then lastly, and possibly most importantly, we're going to work with your specific needs for your module. So you aren't constrained to the generic shell, the standard shell. If you have specific needs that modify that geometry, we're going to validate against that as well. And we're going to provide the communications path back for this data for the order and fulfillment process. So we've talked about the data. We've talked about what we want to do. If we're really successful, we should be swimming in beautiful custom Ara shells that we've only touched the surface of here in this slide. Okay? So if we have all this data and we want to make these, how are we going to make them? Because I'm not aware of a person
So my name is
today
Jeff Blank. I'm
that
with
will do
3D
that.
Systems. And so the 3D Systems Corporation is delivering the additive manufacturing 3D printing technology for the Ara project. The challenge in all of these things are the material properties, making them robust and durable. We're just starting to head down the path of getting the necessary color and vibrancy. And one of the bigger challenges is doing all of this at the rate, being able to make thousands of these enclosures in a given day of production.
So that's a little introduction that was done by Jeff Blank, who's 3D Systems program manager for the Ara fulfillment process. And he's here today. He'll be at many of the other future events. Feel free to directly talk to Jeff if you have specific questions that don't get answered today. So Jeff's project, the Ara Fulfillment Project, is a system that can handle a library of materials. So let's start with what are the building blocks that we're going to need in order to create those objects, those three pillars we talked about earlier. So we're going to need pigmented materials. We're going to need low durometer materials. We're going to need tough materials. We're going to need clear materials. They're going to need to be biocompatible. They're going to be conductive. Okay? So this is work that's being done now for the fulfillment process, for the system. Because this library of materials doesn't exist in any one system today. That system is going to encompass both additive, subtractive, potentially pick and place, other functions that are required to fulfill the Ara customized shell process. So it's not just a single printer, but it's a system, the manufacturing cell. And you're probably wondering why I brought my Gatorade. It's not just because I get thirsty giving these talks, but I wanted to give a demonstration of the throughput potential of this system that we're building. Now, a lot of you have worked with systems that do 3D printing. You kind of know the speed, the volumetric ability of those systems. So the Ara system is going to have the potential of 6.8 or 0.68 liters in a minute. So that's kind of the volume of material that we can put through this system in a minute. I've never seen a system that can do that much material. Specifically, at a voxel size of 22 picoliters, which is one of our targets. So imagine 22 picoliter modules of material, voxels, that we are going to be able to position anywhere in our custom shell and hopefully create the first custom shell that I would like to produce. It's a fish. Those on the team are probably laughing inside because I've brought this up a number of times. But the ability to create a representative model of a fish, other than taxidermy, is this device has that potential. So what did we say the 3 pillars were? Color, the ability to put color down. Clear materials. We're going to have textures. You see textures in this. We also have conductive. The veins can be conductive. So we have the ability, for the first time, to do a good job of representing a model of a fish directly out of this device. So when I'm able to make this first module for myself, I'm going to be pretty confident that you're going to be able to make custom modules that will fulfill your aspirations for the program and your desires for Ara and the program. So, thank you very much. Any questions in the room or? Oh. Yes, sorry.
So with 3D printing, what's the comparison to the structural integrity of actually manufacturing devices to Scott's point earlier on the hollow blocks of design, cheaper build, right? It's pounds. What does the structural integrity look like in terms of that design? Just the same as pouring metal into a box shape and letting it cool and all solid in that building process? Are there weak points in it?
So that's a great question. The Ara fulfillment will not include metals initially.
Can you repeat the question since you're on live stream?
Oh, sorry. So the question was, how do the materials of the Ara fulfillment compare to conventional processes like metal that you would put into a mold? Is that?
Yeah, or plastic.
Or plastic. Yeah. So the initial Ara fulfillment will only be plastics. The physical properties, so one of the types of materials we're developing is tough. So this is where we want to approach the modulus of thermoplastics that you're used to. So there's things like ABS, polycarbonate that are conventional in these types of electronic devices. So we're developing formulations that are going to approach those types of materials for this process. But they're not going to be fabricated the same way, so they will have slightly different characteristics physically. Does that answer your question? Yeah.
How many sites are you going to put printers at? And have you decided where you're going to put the physical printers? Are there going to be printers various places in the world, or just one site initially?
So that's a business question, and specifically for our partner, and I don't think at this time they've made those determinations. But we will be doing at least one. Right. Thanks. Go ahead.
Earlier mentioned conductive printing and pick and place. The first thing that I imagine is printing circuits and dropping in components. What kind of extent have you explored with this pick and place that you mentioned?
So pick and place, not necessarily of circuits. So as I said at the beginning, we are not going to be fabricating the circuit for the modules. But we have other potential needs to put things there. I can't go into a lot of the details of what those would be, but you can think of metal mechanical objects potentially. You can think of fibrous materials. You can think of other things we'd want to incorporate in custom shells potentially. So both the subtractive elements, the pick and place elements are opportunities. They're not hardly defined in the spec today.
Thank you.
Okay.
You mentioned the custom types of modules that people are going to have, like such as the ones that extend beyond the top and bottom of the device. Are you planning on printing for all of these different types of modules?
That's a great question, because we're envisioning things that might need lenses, electronics, metal objects. So as I was just saying a moment ago, we want to have a pathway to fulfill that. It may not be day one that we can fulfill highly complicated shells that require other elements, but we want to. So we want to be able to have that IR module be as decorative as the rest of the modules. We don't want it to have to be a standard module in a monotone. So it's something we're working on very hard.
Hi.
Yes.
By the way, fish was beautiful. Another thing, if you have like the case for the battery module, how much the heat will affect the module? Like, will it last like 6 months, 1 year, unlimited? Is there an effect of heat on the 3D printed material?
So, shells, the covers for modules, the lifespan of those is not in the spec right now. We don't know. I mean, we know we want people to be able to take them on and off, especially old girlfriends, right? Which somebody talked about earlier. The longevity of that cover. So there may be special covers that may have a shorter lifespan or may need replacement that is less than what you imagine in a 2-year cycle today. But those things haven't been determined at this point.
Okay.
But that's a good, you're definitely thinking along the right lines because batteries are going to generate heat. And again, we need to be able to accommodate that heat.
Thanks.
Any other questions in the room? Yes?
Yeah, quick question from like a supply chain management perspective. So if we're building modules that have pieces that go into the Z space, right now you've covered if people go online and order them, if they go to the website and we custom design them. What do you envision working with module developers on us or even you guys getting the parts and having to print onto them, right? Because if you do a model where it has a piece where it won't allow the snapping, you'll have to literally have those pieces in the 3D printer, have it print on. What thought have you guys given to that, or what's your plan around non-snap-offable, custom colors, shapes, materials?
Yeah, I think we're going to be able to bring a lot more clarity to the next module developer conference because not only do we want to support you for production, but what about your iterative prototyping process as you're developing your modules? So we definitely are going to use printing to support the community, and you're going to have an opportunity to help us determine what's of value to module developers that we will build into this fulfillment process. So it's not a one-time specification. This is going to be a living, evolving component of the MDK. Okay? Is that okay? Yes?
Is it going to be possible, I know you've showed mostly flatter things. Can the current printing system print things that are relatively tall, or is there a certain cutoff limit that's...
I definitely plan on having the fish stick up. So yes, so the printers have the ability to go beyond that plane of the endo. And we definitely envision that. I think I may even have a couple shells here that go up and beyond that plane. And as you see in the specification, there's guidelines on how to go up beyond that plane of the endo.
So the printers will be able to go all the way up to the guidelines of where the endo can physically extend?
Correct.
Hi. If you want to print something with a button and you want to have the design that you've printed onto the shell go over the button, right? So the button's generally a separate thing that can move in and out. Do you have an accommodation for that at this point?
Great question. Buttons are a part of Ara. We are contemplating how we can do that, not only for modules in the standard form, but what customization we can enable. So it's not covered today in the MDK, it's not covered in specificity, but it's on our minds. Okay. Yeah. Because it's very tactile, right? Right. Exactly. Great. Another question.
One more question. Can you go in a little bit into some of the materials that you're going to be printing? I know there are a lot of popular plastics today. Can you go a little bit into what kind of stuff you have in mind, material-wise?
Other than the descriptions I've given you, I can't.
Okay.
I mean, those are the characteristics we're going for.
Okay.
We are in an active program of formulation, reformulation, test to get there.
What about how you're going to be outputting so much material from these printers? I imagine with one single filament, it might be difficult to do that much material. Can you talk about how that happens?
Not today. We can't get real specific about the fulfillment device because it's still in flux. We're not trying to be elusive, but it's not nailed down enough that we can really talk about it today.
Rats. Well, thank you very much.
No problem. Thank you. Any other questions? Well, I want to thank all of you for listening to us and look forward to your ideas for shells. Thank you. It'll be.
So given that we're running a little bit early, we're going to take a little break, and Derek is going to go on at 4 o'clock as scheduled for people who are doing parallel tracking, so that we'll start on schedule. Thanks. Well, I think the timer is going to go to the duration of 60 in a second. All right. So I would like to introduce our last speaker in this track, who is the head of the RF design team on Project Ara. As I mentioned in my opening remarks, active RF emitters are not yet part of the MDK, which is why you didn't hear from Derek in the MDK run-through session yesterday. But it's something that we're actively working on and are trying to innovate in that space, because obviously antennas for a user reconfigurable device are something quite new. And so Derek is the co-founder and CTO of a company called X5 Systems. And with that, I'll turn it over to him for a riveting presentation with some hardware, which is the best kind. So thanks,
very
Derek.
much. Yeah, so I'll be talking about how we're getting to active and even passive RF modules. First of all, brief introduction, and then talk about the RF design space. One of the biggest issues, of course, is where do you put antennas on a phone with this kind of a slim profile? Then talk about the process that you would use to get to your RF modules, and then some of the tools that are in development right now to help you get there. Current mobile phones have a very static and predetermined RF configuration. Not only, the rest of the hardware, but in particular, you've got the antennas that are very carefully designed and tuned into that platform, as well as things that are considered like power levels, SAR, efficiency. And all those can be predetermined at the factory in a normal phone. In this case, in the Ara platform, you have a great deal of flexibility in configurations, upgrades, manufacturers. Things can happen at will and at any time. Also complicating the issue is that each module is usually electrically small compared to the wavelengths that are being used. So even with these challenges, the objectives are to allow for interchangeable functional modules and to create a trivial barrier to entry, even for RF modules. This is a very great technical challenge. And also to reduce the design build iteration requirement that happens, especially with things that involve antennas and something that couples to the platform. Now, as you've heard, of course, the Ara design space has these different module sizes, the 1x2, the 2x2, and the 1x1. And of course, each unit is 20 millimeters. Modules can be flexibly placed, and also we've just heard from 3D Systems about customized production. The shells are able to be opened and replaced by users, and in fact, you may want to let them do that as much as possible in case they've printed a girlfriend onto that shell, as we've heard in previous talks. Also, one thing that we're looking at is antennas may be embedded into the shells themselves. And this is a very interesting, exciting development, but it can be also some more challenges as well. And we're also looking into rapid module design using automated design tools that I will talk about. Now, not only can you have a single platform with different locations for your modules, you also have multiple platforms. The 3 different sizes that are planned at this point each have their own challenges. And even though you see, the 2x2 module may be very tempting for an RF module designer to try to grab onto, you probably will have a hard time getting people to put their radio in the 2x2 slot. A 1x2 slot seems to be more of the desired form factor, because it's also in every phone. Now, there's another aspect of this that's actually very exciting for RF modules, and that is you may be able to expand beyond the form factor limitations. Now, for say you wanted an HD TV receiver or something like that, having an antenna that could extend beyond the platform could be very exciting. The caution, of course, is you need to make sure that provides some sort of competitive advantage, that it's not just a protruding antenna because it's easy. Some of the design tools that we'll provide are able to get size-reduced antennas and very thin antennas, and you should probably try making it fit into that form factor as much as possible. Now, we are synthesizing some prototype antennas right now, and I will be showing those to you on the Elmo soon. We're looking at various bands, cellular bands, Wi-Fi, GPS, and others. And we're looking at various locations, 3 locations primarily: module boards, module shells, and the endo frame itself. Let's see. Now, one of the things about having an antenna embedded in the module shell is, how do you connect to it? You'll see some hardware, some lab hardware up here that has coaxial cable pigtails. This is probably not the method you'd want to use. You would want to use something like spring pins or some other attachment method that provides some reliability and flexibility for the user. So to start in on where do you put the antennas, one of the first places to put the antenna is as a layer on your RF module. What you can see is this Wi-Fi module is broken out on this chart, and it has an antenna as a layer above the safety shield. You could even envision gluing that down or adhering it and putting some epoxy down on top of the shield to make sure the antenna doesn't move. Nice thing about that approach is that if the user takes off the cover, puts on a different one, they don't have to worry about, do they have an antenna in the cover, do they have to do anything special, and they really can't mess with your design very much. The other thing that's very nice about it is the FCC in particular likes having antennas that are not user modifiable, that are not, don't have connectors that they can take off and put on something different. So this makes the certification process likely easier. Of course, the disadvantage is you have a very limited space in which to put the antenna. So that creates some other problems. Antennas are difficult in that, unlike, say, with RF circuits, integrated circuits can usually be size reduced just with better photolithography, better equipment. With antennas, you run into a physical limitation. There is only so far you can reduce an antenna, and you really can't go any further. And the software tools that we are developing are intended to get you as close to that physical limit, that practical physical limit as possible. However, you do have to keep that in mind when you're looking at antennas. Now, this Wi-Fi antenna that was just on the previous slide, give you a little bit more detail on that. It was created by our software. It was created using a genetic algorithm and other AI techniques. We put in requirements into our system and got this antenna out. It was not intentional that it looks like a G. It just happened that our system produced that. Must have known it was working for Google, but it's a very interesting design. The pattern is pretty omnidirectional, as you can see on the right side of the chart. In the middle is the chart of where the field concentrations are. Now, this is important for things like SAR, specific absorption rate. It's an FCC requirement that you not have too much. One issue with this is that we have a hot spot in a very localized region. And what we may need to do as we go forward, this is a prototype, we may need to optimize that a little bit more if we do have a SAR issue there. But that is one of the design considerations that you'll have to take into account. Now, we've also worked on a GSM antenna. This is a 1900 band GSM antenna. It's sized to fit on a 1x2 module. And it's got a kind of blobby pattern that seems fairly desirable for the platform. And the currents you can see are somewhat more spread out. That's good. However, you also have a lot more power that goes into a cell phone antenna like this. So we still have yet to see if the SAR requirements are going to be met. Now, another place to put an antenna like that GSM antenna is actually in the shell itself. Something that 3D Systems has been pursuing is putting conductive ink right into the 3D printed shell itself. And I'll show you a couple of the pieces in a couple of charts here. But that seems to be very promising in giving us not only a way to attach the antenna that isn't, that's part of the structure that's already there, but also a way to get a little bit more volume. One of the big issues with these modules is they're very height limited. The Z direction is, I believe, only about 4 millimeters from top to bottom, although you have to check the MDK to be more certain of that dimension. But with that limitation, the design and optimization process. Now, that Wi-Fi antenna that I was just showing you, it is actually a dual band Wi-Fi. We have 2 different patterns. Both of them are fairly broad in coverage. But you can see we do actually have a dual band performance out of this antenna. The hotspots are different at 2.4 gigahertz and at 5.6 gigahertz. And that is indicative of an antenna that's working at 2 narrowband frequencies. I'm going to show you that because later we'll talk about an antenna that seems to be a little bit more broadband. And that leads me to putting the antenna in or as part of the endo frame itself. As we are going forward, we're seeing that having more space in the module just is not, we just can't make the board any thinner. We don't want to extend beyond the frame of the phone. But we have this big piece of metal that if we can just find the right place to feed it and perhaps add a few little structures into it, we might have a chance to get some very good performance using the entire endo as an antenna. And just to say, in this case, you see the 2 small gray areas. That might be a place where you would have, say, spring pins or some other contact method that you would come out of your RF module and you'd contact the frame in those particular locations to resonate at the frequencies of interest. Now, we've looked at putting antennas into the endo, basically just subtracting parts of the endo, putting a slot in there, and seeing if we can get it to resonate at the right frequency. And this particular experiment showed that we've got some pretty decent performance at both 900 megahertz and all the way up to 2 gigahertz, and you'll see that the hotspots are actually fairly uniform between those two frequencies. Nice thing there is that means we may have a possibility for a broadband antenna. The issue, of course, is that we are feeding a simplified endo. That hole goes all the way through. But so it doesn't include the it's like the battery that's in between. It doesn't include the display at this point. So these are things that we're going to have to look at as we get more accurate. One of the other very interesting characteristics that we're looking at is feeding the endo using characteristic modes, and this is being done at Carnegie Mellon primarily by Irina Brinster, who's in the audience. And we're looking at using this endo frame as a radiator of its own without necessarily cutting any additional holes, just finding the right places to put our wires. And the key is finding the best feed points. Think of ringing a bell with a hammer. You know, if you find, there are certain places that it's going to just, the energy is just not going to go into the ringing mode. It's just going to kind of dissipate. But if you find that sweet spot, you'd be able to really make the tone very loud. And that's the right idea. That's the idea that we're trying to pursue here, is finding those characteristic spots that we can hit with an RF signal. So, for instance, looking at the entire endostructure as a Wi-Fi antenna, finding a couple of those feed points in the colored red and green there gives us a good match to a 50 ohm RF circuit, as well as a higher radiated power than other positions on the phone itself. So these are some of the explorations that we're undertaking in order to come up with the proper placement for antennas. If we could switch to the Elmo at this point. Yeah, terrific. Yeah, I wanted to show you some of this hardware. What we have is okay, it's sideways, this way, good. Now, it turns out that our software not only produced an antenna with a G, but also an antenna, another Wi-Fi antenna with an A. I didn't direct either one, but it obviously has a sense of humor. It either stands for Google Ara or genetic algorithm. Not sure which. It's like it's trying to tell me something, though. Getting there, yeah. But the interesting thing is that even with the same specifications, we're able to sometimes get different antennas. For instance, in the slides I showed you, this little spike here seems to be a hotspot. And if that became a problem for SAR, I'm thinking that this A antenna might very likely have spread the currents out a lot more, even though it's a little bit larger, and so is kind of maybe less desirable from a geometry standpoint. That may be tolerable if we can reduce the field concentrations. We've also, here's the example of the GSM antenna, and taking an example cover, you can see it's fit to that size. The issue there is that whether it would need to be actually embedded in the material, or whether it would be, say, a separate piece of flex circuit. There's quite a few different ways that we can envision actually attaching the antenna to your RF board. Here's an example of the dual band Wi-Fi antenna. This is also printed. This is printed using the silver ink technology and onto the 3D material, and that is undergoing testing at this point as well. Now, also to show you this is an example of an Ara endo frame with a few example modules in it. Obviously, this is not the final form at all, and there's a lot of pieces missing, but it gives you an idea of what we might be able to do in terms of putting holes or contact points into strategic locations to allow the right kind of RF communications. All right, thank you. Now, the process for developing a new RF module starts with design, of course, and the design tools that we are providing or will be providing for rapid development. Things like module design. You had an opportunity to hear from the Metamorphosis team this morning, and also this afternoon they did a demo of their software tool chain to make module design much less painful. And also, we have an antenna synthesis tool that I'll talk about in a moment that will be part of that tool chain that will allow you to generate antennas if they haven't been generated already for, say, new applications or for something that has a slightly different geometry than what has been done before. We're looking to have EMI simulation and analysis and SAR simulation and analysis tools to help you in your module design process. And of course, after that comes testing and certification. Certification was addressed by Elwin yesterday. And just back on that chart, that photograph is this is the official way that the FCC and other organizations will allow you to certify a device for SAR in this particular case. What that is it is filled with a fluid, a simulant of human tissue, and a probe is pushed down into it by a robotic arm and is checked along different points to see if you have put too much energy into this head model or this head phantom, and to see if you're meeting requirements for safety. It is a long process, very time-consuming, and so we are looking into ways to speed this up, especially to get you feedback before you put in any kind of expense into a test lab to see if there are ways we can accelerate this process and make it less expensive prior to final certification. Now, this is a graphic of the Metamorphosis tool chain that allows you to go from basically concepts and components into simulating things like how it will behave in a logical sense and in a electronic sense and also in a physical sense. Things like thermal performance and also RF performance, and that's where our tools come in. Just to give you a little bit of heritage on antenna synthesis, where these designs kind of came from. Back in 1994-95, I was working, just getting started in antennas at an Air Force research lab near Boston. And I and a colleague, Ed Altschuler, who had been designing antennas since the 1950s, we were looking to try to solve some very difficult problems. And simulation tools were not highly trusted back then. And one of the first antennas that came out of using a genetic algorithm to solve a particular broad beam antenna problem, looking to, for those of you who know, trying to capture circular polarization in hemispherical coverage. This is usually done with pretty expensive types of antennas that require some pretty complicated phasing. What my colleague asked was, can we do this with a single wire? And I had just learned about genetic algorithms, and I wasn't sure what such an antenna would look like, but I thought, okay, let's see if this technique can really do a good job. So put some wires into a box, basically, in simulation, and said, okay, algorithm, tell me where those points, how to string up the wire between all these points, and give me what I'm looking for. The antenna that came out was the one on the far left of the screen. And we saw this on the computer screen and said, okay, we're not going to tell anybody about this until we've built and tested this, because no one is going to believe us that this bent wire is going to do anything. So we built it and tested it, and it worked. And then, so that kind of launched this whole technology for us. In 2006, the antenna with the blue background, another crooked wire antenna, was launched on Space Technology Demonstrator for NASA, ST5, carried one of these on each of 3 satellites as a communications antenna. It replaced an antenna that was built using more traditional methods. It was heavier and less efficient and more expensive. And so that really helped us with, now we've got an example of an antenna that was synthesized by computer that actually was human competitive, in some ways even superior. And since then, we've gone on to optimize planar antennas, two-dimensional antenna arrays, traditional types of antennas like the spiral or log periodic, and also really wacky stuff like one that looks like a soccer ball, and all kinds of things in between. So that brings us to the tool that we are developing now, that is actually available online. It is a browser-based tool, uses HTML5. And it allows you to put your specifications into a form that we call a spec sheet. You put in band starts and stops. You can have multiple bands. You can specify antenna patterns, and you can choose from antennas within a library and set geometric constraints. If you don't have any clue what antenna you should be using, you can let the system choose for you, and it will use some expert system methods to come up with some antennas that are intended to help meet your specification. Now, what comes out of that tool is we'll have a number of designs and also characteristics. Patterns, frequency characteristics, like return loss, and a representative model. And you can download CAD files and various simulation tool files, so you can bring them into your own favorite simulation tools and work with them from there. That basically concludes the prepared slides, but definitely open to questions. And if you have any requirements for any additional information, please go to Ara Dev. But thank you very much. So, any questions? Yeah, can you go to a mic?
While he's coming up, Derek, I'll ask a question from the internet that we have here from IRC, from Pedro. He's asking about SAR testing. I guess the comment is that it might be insufficient because it makes some assumptions about just the hands, but doesn't necessarily include the user's head. Maybe can you elaborate on what SAR testing includes and what it looks at?
Right. Let me go back. Well, yeah, thanks. So SAR testing, when it's done at an accredited facility, will include head and hand model, and will include probes to certify that when the phone is held in the sort of canonical positions that you don't violate the safety regulations. It is a slow and expensive process, but true SAR testing will accomplish all of that. Now, what we're looking at, there are rapid scanning machines that are coming online that will allow you to do this much more rapidly. Maybe not completely certified, but gives you a good idea of whether you would pass certification or if you need to go back and refine anything. And we're also looking into computational tools that will give you, again, probably not a certified result, but something that would give you a good idea of whether you're going to have a problem with certification or not. Yes?
Hello? So the genetic antenna is really, really cool. That stuff is very interesting. What kind of things do you think we're going to see as RF modules, you know, at the beginning? Like, do you see anything coming out the gate that will exist, or, you know, besides Wi-Fi, or?
Yeah. Well, the first, you know, at first we're looking at Wi-Fi being the first module that's an active RF emitter. But short term, we're looking at developing a GSM module. Whether that actually gets, you know, both, say, a 1900N and, say, 850 megahertz, we'll see how many bands we can cover in what time. So we're going to do as much as we can, but GSM is our next target.
Thanks.
Yeah, thank you.
So, do you have any thoughts on supporting like the diversity requirements?
Yes. Yeah, especially for LTE has a diversity requirement, and even Wi-Fi modules would like to have diversity if you could get it. So yeah, there are some possibilities. For instance, if say you have the main power antenna being part of the endo frame itself. Say you've put most of your your transmitters connected to an antenna embedded in the endo. You can envision having a cover-mounted antenna as your diversity antenna. Or perhaps, there are other things that we're looking at, perhaps more than one endo-based antenna. There are issues with that, of course, because you have to have transmission lines, and those cause loss, and they may limit where you can put modules, etc. So this is something of an open area, and certainly welcome ideas or suggestions as well. But yes, it's definitely something we're looking at. Yeah.
Hello, my name is Peter. I want to encourage everyone to not only think about the application here as a smartphone, this whole platform and your work as developers, because I'm not one, could be beneficial in very specific areas and very specific tools. For example, I am in a huge need for you guys to come up with a closed circuit wireless network, perhaps Wi-Fi, perhaps something else, that would allow us to bring these devices into rooms and have events that are that need to be, a completely closed group. No outsider should have access to that wireless network because we do voting, we do elections, and these modular devices would, allow us to do that. So, if your first foray into this is Wi-Fi module, great. And just a side question: does that do Wi-Fi direct kind of a thing, or peer-to-peer network?
That I'm not sure the answer to that question. I believe the Wi-Fi design is intended to be in the reference design will be in the MDK in the near future, and that should give you a better insight to that.
Okay. But if you or anybody else wants to make a wireless protocol or wireless module for for the Ara project that does this this kind of closed circuit networking, contact me, or I'm sure that hospitals would have a specialized use for that as well. And mining, we have clients on oil rigs where they do very specialized applications of handheld devices that give feedback. And once again, they don't have any cellular signal in the middle of Thailand's sea. So, you need a very, very specific modules for this. So, thank you.
Thank you. Yeah.
Yeah. Have you done any work trying to analyze, particularly in the case where you have the antenna in the endo, how it's going to interact with the buses and the capacitive pads on all of the modules in terms of injecting power and noise into the bus?
Right. Well, certainly one of the things that they're looking at in the capacitive or non-contact communications is lower crosstalk. And that basically deals with signals that leak out and signals that can leak in to those channels. So at those levels, it's looking, especially since the frequencies that they'll be using are likely to be different from what we're looking at for the cell phone power. We're not anticipating a lot of problems with that. However, that is a very important thing to be checking, and so yeah, I appreciate the comment.
Well, there are also modes where in effects, especially with ferrous materials and that kind of thing, with magnetostriction effects that can mix down RF frequencies into lower frequency bands and cause problems. So I think that's an area ripe for investigation.
Yeah, you need passive intermodulation right on the phone could be nasty. So yeah, these are things we definitely will want to look at, and I appreciate the comment.
Thank you.
Hi, I got another question. My name's Chris. So one thing I've noticed is that and I was just in the power discussion, they were talking about how the power bus can take all different powers from all sorts of things, and I wonder how you think that's going to affect the RF sections of these devices, and if they're, like, what kind of specs, are we going to need additional specifications on what the power can be, or some kind of clarification on that?
I believe that's going to be fairly universal to all modules. It's going to have to power the digital circuitry. I don't think it's going to be all that different because the RF signals are going to be not going to be at DC, where the power is running at essentially 0 hertz, and we'll be looking at things in 700 and up.
Right, but if there's noise on the power line coming in, that can modulate into your signal.
Definitely, you want a good clean signal. So, yeah, it definitely will be another consideration to look into as we go forward. Yeah, thanks. All right, well, thanks for staying to the very last session. I appreciate it. And again, please see me with additional questions if you're live in the audience. So thank you very much.
Thank you, Derek. And so I think that concludes our sessions in the Grand Hall for today. So for the folks in person, we still have the UX session going on in Han across the way. If you want to find out more about the configurator and the experiences we're designing there. For the folks online, I think this is it. We have to say goodbye. So thanks for joining us on the live stream. And a shout out to the IRC guys and folks who have been on IRC. The discussion there has been great and great questions. So thanks for joining us there. And I guess that's it. So thank you, everyone.